The final day of the universe's first rule. Every process seems to have an end. We see it in the small moments of the world around us. Steam rises from a hot surface and vanishes into the air. Ancient structures slowly return to dust. These endings are contained within our own experience of time. But what about the process that contains everything else? The one that includes every star, every planet, and every form of life? Does the universe itself have a final state? For billions of years, a single, quiet principle has governed reality. It is not a rule that was written down or enforced. It needs no enforcement. It is woven into the fabric of existence itself, as fundamental as space. It is the author of the final chapter for every star and every galaxy. This is a journey through that principle, its quiet reign over the cosmos, and the distant, almost unimaginable day when its work is done. This is the story of the universe's movement towards a state of perfect, eternal stillness. This principle has a name. Physicists in the 19th century, studying the movement of heat in steam engines, called it the second law of thermodynamics. But its essence is simpler and more fundamental. It is the law of entropy. Entropy is often described with a single word: disorder. The law states that in a closed system, and the universe is the ultimate closed system, total entropy, or disorder, always increases. It never decreases. This is the steady direction of reality. It is the reason things disperse and decay. It is why a cup of coffee on a table will always grow cold, its concentrated heat spreading into the cooler air until they reach the same temperature. It is why a sandcastle, a structure of temporary order, eventually becomes a uniform patch of sand. The universe itself follows this same principle, just on a scale that is difficult to comprehend. It began in a state of profound order, and ever since, it has been unwinding. Its energy has been spreading out, moving toward a final state of featureless equilibrium. This process is the quiet driver of cosmic evolution. It is the unseen principle that guides the fate of all things. It dictates not just the end of stars, but the direction of time itself. We experience time moving forward because we are witnessing the universe's transition from a state of low entropy to a state of high entropy. It is one of the most fundamental processes in nature, and its story is the story of everything. The law and its nature. To understand the power of this principle, we must first understand why it is so absolute. It is not a force, like gravity, that pulls things together. It is a law of probability. Imagine a new deck of cards, arranged perfectly by suit and number. This is a state of low entropy, a single, specific, highly structured arrangement. Now, shuffle the deck. The cards become mixed. This is a high entropy state. This happens because there is only one way for the cards to be in perfect order, but there are trillions of ways for them to be disordered. The universe, with its countless particles, operates on the same principle. It is simply statistically inevitable that things will move from ordered states to disordered ones. From concentrated to spread out. From specific arrangements to generic ones. When the physicist Rudolf Clausius formalized this idea in the 1850s, he was studying engines. He realized that heat always flows from a hotter object to a colder one, and never the other way. This flow of energy is what allows work to be done. It powers a steam engine, a star, or the processes in our own bodies. But with every transfer, the energy becomes a little more dispersed, a little less useful. The total disorder increases. Clausius gave this increase in disorder its name, entropy, from a Greek word meaning transformation. This law is unique. Other laws of physics, like gravity, appear to work the same forwards or backwards in time. A film of a planet orbiting a star looks plausible whether it is played forward or in reverse. But the second law provides a direction. A film of an egg unscrambling itself looks immediately wrong. This is the arrow of time. It points in the direction of increasing entropy. It governs the largest scales and the smallest. On a cosmic scale, it means that stars must burn out. They are concentrated spheres of low-entropy fuel, and their existence is a process of converting that ordered matter into disordered light and heat, which spreads across space. On a biological scale, life itself is a constant negotiation with entropy. A living organism is a marvel of order. To maintain this order, it must consume energy, food, oxygen, or sunlight. In doing so, it releases heat and waste, increasing the total entropy of the universe around it. Life exists as temporary islands of order, built at the cost of a greater, more widespread chaos. The second law does not need to be enforced because it is a statement about what is most likely to happen. In a universe with an astronomical number of particles and an astronomical amount of time, the most likely outcome is the only outcome. The story of the universe is the story of this principle playing out, era by era, across a timescale that defies human comprehension. The reign of the rule, the stelliferous era. The work of entropy began at the dawn of time. In the first moments after the Big Bang, the universe was incredibly hot and dense. It was also, paradoxically, in a state of very low entropy. It was an almost uniform plasma. While this might sound disordered, in a universe governed by gravity, this smoothness was a state of profound order. It held an immense potential for complexity to form. As the universe expanded and cooled, that potential began to be realized. Gravity pulled matter together, gathering gas into clouds, crushing their cores until nuclear fusion began. The stars were born. The stelliferous era, the age of stars, had started. This is our era. A star can look like a triumph of order, a magnificent structure. But its existence is a perfect demonstration of entropy. A star is a machine for creating disorder. It takes ordered, simple atoms like hydrogen and fuses them into heavier elements. In this process, a tiny fraction of their mass is converted into a vast outpouring of energy, light and heat that radiate into the void. This radiation spreads out, becomes more dilute, and massively increases the overall entropy of the cosmos. The star's light is the price of its own internal structure. For billions of years, this process has filled the universe with light. Galaxies formed as great collections of these stellar engines. On at least one small planet orbiting an average star, the constant stream of energy from its sun allowed for an even more spectacular, though temporary, pocket of order. Life emerged. From a simple cell to the human brain, life is the most complex phenomenon we know. It is a system that actively maintains its own internal order. But it cannot cheat the second law. It can only manage it. Every breath we take, every meal we eat, every thought we have is part of a process that takes in ordered energy and expels disordered waste and heat. We are like whirlpools in a river, maintaining our form for a time as the water flows through us, all while the river itself continues its journey downstream. But the stelliferous era is finite. Every star has a limited supply of fuel. The law of entropy is patient. It waits for the fuel to run out. Our own sun will exhaust the hydrogen in its core in about 5 billion years. It will swell into a red giant, then shed its outer layers, leaving behind a cooling core called a white dwarf. Across the universe, this story will repeat, star by star. The most massive stars have already ended their short lives in supernovae. The long-lived red dwarfs, the most common stars, will continue to burn for trillions of years. But even they are not eternal. One by one, the lights will go out. The great age of stars will give way to a long, gathering twilight. The work of entropy is methodical, and it is only just beginning. The long twilight, the degenerate and black hole eras. After the last star has faded, the universe will enter a new, different age. The story is not over. The cosmos will be cold and dark, but not yet still. This is the degenerate era, a period that will last for trillions upon trillions of years. A length of time so vast that the entire age of stars feels like a single moment. The universe will be populated by the remnants of stars, white dwarfs, neutron stars, and black holes. The white dwarfs, the cores of stars like our Sun, will continue to radiate their leftover heat. But with no fuel to burn, they are only cooling. Over perhaps 100 trillion years, their glow will fade until they emit no visible light at all. They will become black dwarfs, cold, dead crystals of matter drifting through the dark. No black dwarfs exist yet. The universe is not old enough for any white dwarf to have cooled completely. The neutron stars, the dense corpses of more massive stars, will also cool. The planets that once orbited these dead stars will have been flung off into the darkness. The galaxies themselves will begin to dissolve as their stellar remnants are slowly ejected by gravitational encounters. But even these dead objects are still pockets of highly ordered matter. And the process of increasing entropy is not yet complete. A new, almost impossibly slow process is predicted to begin: proton decay. Some theories in physics suggest that the particles making up atoms, protons and neutrons, are not truly stable. They are just incredibly long-lived. Over a timescale of perhaps 10 to the power of 36 years, protons are expected to slowly decay into a flash of lighter particles and radiation. This process is entropy at its most patient. Imagine waiting for so long that the very atoms making up a cold, dead star begin to unravel. One by one, over spans of time that make the current age of the universe seem insignificant, the particles within the black dwarfs and neutron stars will dissolve. The great stellar graveyards will evaporate into a thin haze of photons and other particles. The last traces of the matter that makes up our world will be erased. What is left? After all normal matter has dissolved, is the story finished? Not quite. One type of object will remain, a final monument to structure in the cosmos: black holes. This begins the black hole era. For a time, they will be the only large objects in the universe. It was once thought that black holes might be truly eternal, a final loophole in the law of cosmic decay. But then, a profound discovery showed that even black holes must obey the principle. They are not eternal. They evaporate. This process is known as Hawking radiation. It is a subtle quantum effect at the event horizon. In empty space, pairs of virtual particles constantly appear and disappear. If a pair appears at the edge of a black hole, one particle might fall in while the other escapes. To an observer, it looks as if the black hole has emitted a particle. Because mass and energy are equivalent, this slow leak of radiation causes the black hole to lose mass. The process is astoundingly slow. A black hole with the mass of our Sun would take an estimated 10 to the power of 67 years to evaporate. A supermassive black hole could take as long as 10 to the power of 100 years, a number known as a googol. This is a timescale so vast it renders all previous cosmic history almost meaningless in comparison. But the second law is in no hurry. For googols of years, the universe will be a dark, empty space, punctuated only by these solitary objects. And one by one, over these unimaginable eons, they too will dissolve. The smaller ones will vanish first, their evaporation accelerating as they shrink. The supermassive ones will hold out the longest. But their reign, too, is finite. The principle is absolute. And its final day approaches. The final day. Imagine the universe in the last moments of the black hole era. Space is stretched, cold, and almost perfectly empty. For a googol of years, the only landmarks have been the supermassive black holes. Now, almost all of them are gone. They have slowly radiated away their mass, returning their energy to the universe as a faint bath of particles. But one remains. The last black hole. It may have once been at the heart of a great supercluster of galaxies. For an eternity, it has been the only significant object in its observable universe. But it, too, is nearing its end. As its mass has dwindled, its rate of evaporation has accelerated. In a final, quiet burst of energy, The last bastion of structure vanishes. The last piece of organized matter in the universe dissolves. The final day has arrived. The work of entropy is complete. This is the dark era. The universe has now reached the state that some physicists called the heat death. The name is slightly misleading. The universe is not hot, it is just fractions of a degree above absolute zero. The death refers to the end of all process, the end of all change. The universe is now a vast, endlessly expanding void, filled with a uniform, incredibly dilute soup of photons, neutrinos, and other fundamental particles. All stars and galaxies are gone. All black holes have evaporated. All atoms have decayed. There are no longer meaningful differences in temperature or density from one place to another. Energy is perfectly, evenly distributed. This is the state of maximum entropy. It is the ultimate state of disorder, not because it is chaotic, but because it is perfectly uniform. There is no structure, no complexity, no information. Every arrangement of the particles looks the same as every other. There are no more ordered states for the universe to move toward. In this final state, something profound has happened to time. The arrow of time, which exists because of the universe's journey towards higher entropy, now has nowhere to point. When every moment is statistically identical to the one before it, does time still have a forward direction? The great cosmic process that began with the Big Bang has finally wound down. Nothing happens, and nothing will ever happen again. This is the quiet conclusion of a fundamental principle that has guided the cosmos to its final, stable state. An eternity of unchanging stillness. Conclusion: we stand, in our minds, looking out at this quiet, timeless state. The story of cosmic evolution, of stars being born, of life emerging, of discovery, is over. It was a temporary spectacle that occupied an infinitesimally small fraction of all of time. Faced with this vision, it is easy to feel a sense of futility. If the inevitable destination is an empty void where nothing happens, what was the point of the brief flicker of complexity? But perhaps that is the wrong way to look at it. The law of increasing entropy is not an antagonist in this story. It is the context that makes change possible. It drives the flow of energy that powers stars and allows for life. Without entropy, the universe would be a static, frozen place where time has no meaning because nothing could ever change. The existence of order and life is not the default state of the cosmos. It is a temporary and breathtakingly beautiful exception. We are the products of a universe that began in a state of exquisite order, with the potential for complexity embedded in its initial conditions. For a finite, precious span of time, the universe is able to build structures, create complexity, and even, on at least one world, become aware of itself. The knowledge that the story has an ending does not make the story meaningless. It makes the moments of complexity all the more precious. Our existence is not a struggle against an unbeatable foe. It is a temporary performance of order and creativity, made possible by the very laws that will one day bring it to a close. And so, as we look out at the night sky, we are not just looking at a system winding down. We are looking at the story of which we are a part. A story made possible by the second law. It is a journey from a fiery, ordered beginning to a cold, still end. And everything in between, every star, every world, every life, is what gives that journey its meaning. The final day is not a tragedy. It is the quiet, peaceful conclusion to the greatest story ever told. Thank you for joining us on this journey to the end of time. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. Until next time, keep looking up. The one law holding reality together. You exist because of a promise. A single, unspoken agreement the universe made with itself when time began. A foundational rule that dictates, well, everything. This promise says the structure of an atom isn't a friendly suggestion. It says gravity isn't up for negotiation. It says that stars will burn, light will travel, and the very fabric of reality will hold itself together. Everything you can see, everything you are, is built on the simple fact that this one cosmic law has held true. But what if the universe is having second thoughts? What if, after 13.8 billion years of keeping its word, this foundational agreement is starting to fray at the edges? It's a question that goes beyond science, right into existential dread. Because if the one law that holds everything together is starting to unravel, what happens to everything? And what happens to us? The cosmic agreement on a knife's edge. To get a handle on this one law, you first have to appreciate the impossibly delicate balance it maintains. See, our universe doesn't just exist, it performs a constant, cosmic balancing act. The fundamental forces and numbers that govern reality seem to be fine-tuned, with a precision so staggering it's hard to wrap your head around. It's like the universe is a perfect symphony, and if a single instrument was just a tiny bit out of tune, the whole thing would collapse into a mess of screeching noise. Let's start with gravity. We feel it as this powerful, constant force. It keeps our feet on the ground, holds the moon in orbit, and wrangles 100 billion stars into our Milky Way. But on the cosmic scale, gravity is astonishingly, almost comically, weak. The electromagnetic force, the one holding the atoms in your body together, is about 10 to the power of 36 times stronger. That's a 1 with 36 zeros after it. If you've ever used a cheap refrigerator magnet to pick up a paperclip, you've watched a tiny bit of metal defeat the gravitational pull of an asterisk entire planet. And this incredible weakness? It's the secret to our existence. If gravity were just a little stronger, stars would burn through their fuel millions of times faster, snuffing out long before life had a prayer of evolving. The universe would have been a brief, brilliant flash, followed by an eternity of cold and dark. But if gravity were just a tad weaker, the clouds of gas after the Big Bang never would have clumped together. No galaxies, no stars, no planets, just a thin, boring soup of hydrogen and helium, forever adrift. The number that defines gravity's strength is so precise that if you changed it by just 1 part in 10 to the power of 60, that's a 1 with 60 zeros. The universe as a home for life would simply cease to be. But this balancing act goes way beyond gravity. Take the strong nuclear force, the powerhouse that glues protons and neutrons together inside an atom. It's the strongest of the 4 forces, but its power is also on a knife's edge. If the strong force were just 2% stronger, pretty much all the hydrogen in the early universe would have fused into heavier elements. But hydrogen is the main fuel for stars like our Sun. Without it, the long-lived, stable stars we need for life couldn't exist. On the flip side, if the strong force were 2% weaker, protons couldn't stick together at all. Hydrogen would be the asterisk-only element in the universe. No carbon, no oxygen, no iron. No planets, no people, no complexity. The list just keeps going. The mass of the neutron, the energy level of carbon, the speed of cosmic expansion. Tweak any one of them by the smallest fraction, and the rich, complex universe we live in just vanishes. This incredible fine-tuning is the first part of the universe's promise, a promise of stability. For billions of years, that promise has held. But it forces a terrifying question. What is this agreement actually written on? Where do these unchangeable numbers and laws come from? And what guarantees they're truly permanent? The foundation of the agreement, the quantum vacuum. For centuries, we thought of physical laws as being imposed on the universe, like a divine edict. But modern physics paints a much weirder, more intimate picture. The laws aren't just in the universe. In a way, they are the universe. And they bubble up from a source that is as invisible as it is fundamental, the quantum field. The easiest way to picture this is to stop thinking of particles as little solid things. Instead, imagine the entire universe is filled with invisible oceans. These are the quantum fields. There's an electron field, a photon field, a quark field, one for every type of particle. What we call a particle, like an electron, is really just a little ripple, a tiny excitation, in its field. A wave on its ocean. When two particles interact, it's just their fields rippling into each other. The laws of physics, how these particles behave, are just the built-in properties of their fields. The strength of electromagnetism is a property of the photon field. The mass of an electron is a measure of how much the electron field gets dragged by another, all-pervading field, the Higgs field. The discovery of the Higgs field was the key that unlocked this whole perspective. For decades, nobody knew why some particles have mass and others, like photons, don't. The Higgs field theory, proven by finding the Higgs boson at the Large Hadron Collider, gave us the answer. The Higgs field fills all of space like a kind of cosmic molasses. As particles move through it, some are dragged on more than others. That drag is what we measure as mass. A photon doesn't feel the Higgs field, so it has no mass and zips along at the speed of light. A top quark interacts with it a lot, making it incredibly heavy. This gets us to the most fundamental idea of all, the vacuum. Classically, a vacuum is just empty space. Nothing. But in quantum field theory, a vacuum is the lowest possible energy state of all those quantum fields. It's the state where the oceans are perfectly calm. No ripples, no particles. This is the quantum vacuum. But calm doesn't mean zero. The quantum vacuum is seething with a baseline energy that underpins all of reality. The value of this vacuum energy is what sets the properties of the fields, and therefore, it's what sets the values of all those fine-tuned numbers we were just talking about. The quantum vacuum, this rock-bottom energy state, is the foundation. It's the bedrock on which the entire agreement of physical law is built. The precise strength of gravity, the strong force, the mass of every particle. They're all just consequences of the specific energy state of the vacuum we happen to be in. For 13.8 billion years, this foundation has seemed unshakable. But what if it's not? What if the lowest energy state isn't truly the lowest? What if our entire reality is balanced in a state of false stability? The second thoughts, the horror of vacuum decay. This is where the universe's second thoughts come into play, and it's one of the most terrifying ideas in all of physics, the concept of a false vacuum. To get it, let's use an analogy. Imagine a ball resting in a little dip on the side of a massive mountain range. For the ball, that dip is its low point. It's stable. Nudge it, and it will roll back to the bottom of its little valley. From its limited view, it has reached its ultimate state of rest. But we can see the whole mountain range, and we know there's a much deeper, much bigger valley far below. The ball is stable, but not perfectly stable. Its position is what physicists call a false vacuum, or a metastable state. The true vacuum, the real ground state, is down in that deep valley. Now, what if our entire universe is that ball? What if the energy state of our vacuum, the one that sets our life-giving laws of physics, isn't the true ground state? What if there's a lower, more stable energy state the universe could fall into? According to quantum mechanics, that's a real possibility. And the way it could happen is through something called quantum tunneling. In our everyday world, to get that ball to the deeper valley, you have to push it over the hill separating them. You need energy. But in the weird world of quantum mechanics, there's a tiny, but not zero, chance that the ball could just spontaneously disappear from its valley and reappear in the deeper one, without ever traveling over the hill. It can tunnel through the energy barrier. If our universe is in a false vacuum, then at any moment, at any point in space, there is a random, unpredictable chance that a small patch of vacuum will quantum tunnel to the true vacuum state. If that happened, a bubble of this true vacuum would pop into existence. This bubble wouldn't be empty. It would be a region of space where the foundation of reality has changed. Inside, the Higgs field would have a different value. The baseline energy of all the quantum fields would be lower. And as a result, the laws of physics as we know them would be gone. This bubble of new physics would expand outward in every direction at the speed of light. You would never, ever see it coming. The moment its edge touched you, it would be over. The new, lower vacuum energy would mean the fine-tuned numbers that hold our world together would instantly change to new, random values. The electromagnetic force might change, causing atoms to fly apart. The strong nuclear force could change, causing every atomic nucleus to either tear itself apart or crush itself into some bizarre new matter. The very rules for chemistry would be rewritten. Your body, the air, the earth, they would cease to exist in any recognizable way. They would be instantaneously transformed into a chaotic blast of energy and alien particles governed by alien laws. It's a destruction so total, it's hard to even describe. It's not an explosion destroying things. It's the rewriting of the very rules that allow things to be. It's the universe deleting the source code of reality and replacing it with something else. From the outside, you'd see a sphere of perfect nothingness expanding and eating everything it touched. From the inside, there would be nothing. No time, no consciousness, not even a fraction of a second to realize what was happening. The end wouldn't be a bang or whimper. It would be the period at the end of a sentence you never knew was being written. This event, vacuum decay, is what it looks like when the universe's promise phrase completely. It's the universe having a second thought, and acting on it with absolute finality. The idea that our entire existence hinges on a random quantum dice roll is unsettling, to say the least. It forces us to confront how fragile our place in the cosmos really is. We build our lives assuming the ground beneath us is solid, but physics points to a reality where the very rules of the game might be a temporary illusion. If grappling with these cosmic stakes is as fascinating to you as it is to me, consider subscribing. We dive into these huge questions every week, trying to make sense of our place in the universe, and hitting that button is the best way to make sure you don't miss what's next. So, back to the big question. Could this actually happen? The evidence and the search. Is reality on the brink? This whole vacuum decay thing might sound like a ghost story for physicists, but it's not just speculation. The stability of our universe is a real, testable scientific question, and it's one of the hottest topics in particle physics. The fate of the universe, it turns out, might depend on the properties of two specific particles: the Higgs boson and the top quark. Like we said, the Higgs field gives particles mass. The Higgs boson is a ripple in that field, and its own mass is a critical clue. The top quark is the most massive fundamental particle we've ever found, which means it has the strongest interaction with the Higgs field of any particle. The relationship between the mass of the Higgs boson and the mass of the top quark is the key to figuring out if our vacuum is stable. Think of it like this. The top quark's heavy mass acts like a destabilizing force, trying to pull the energy of the Higgs field down. The Higgs boson's own mass acts as a stabilizing force, trying to prop it up. The fate of the universe hangs in the balance between these two. For years, we didn't know the Higgs's mass, so we couldn't be sure which force was winning. But since its discovery in 2012, and with incredibly precise measurements of both particles from the Large Hadron Collider, we can finally do the math. We can plot our universe on a phase diagram of stability. The results are both fascinating and deeply unnerving. Based on the best measurements we have, our universe sits remarkably close to the line between being absolutely stable and being unstable. The numbers put us in a state physicists call metastable. This means our universe is not eternally stable. We are, in fact, living in a false vacuum. However, the energy barrier, that hill separating us from the true vacuum, is also calculated to be very, very large. So while a bubble of true vacuum could theoretically form, the odds of it happening randomly are incredibly low. The calculated lifetime of our metastable universe isn't just billions of years, but trillions upon trillions of years. Far, far longer than the 13.8 billion years the universe has been around so far. So, on one hand, our measurements tell us the foundation of reality isn't absolute. The promise isn't forever. On the other hand, it seems the promise is good for a very, very long time. This is where the idea of the law, fraying, comes in. The physics isn't a slow decay, it would be sudden. The fraying is happening in our confidence. For all of history, we assumed the laws of nature were set in stone. Now, we've measured the very numbers that tell us those laws might be temporary. Our knowledge has led us to the edge of a cosmic cliff, and while the ground feels solid for now, we're suddenly aware of the dizzying drop. Of course, there are catches. These calculations are based on the standard model of particle physics, and we know that model is incomplete. There could be new particles or forces out there that change the math completely. Theories like supersymmetry, if proven true, could introduce new particles that have a stabilizing effect, potentially making our vacuum perfectly stable after all. Until we have a final theory of everything, we won't have the final answer. The search for it isn't just about finding new particles. It's about taking the ultimate temperature of reality and asking the most fundamental question there is our home built on rock or on sand? The philosophical implications, meaning in a metastable world. What does it mean to live in a universe that we know, on some level, is temporary? What does it do to you to learn that all of this, every star, every galaxy, every human achievement, could be resting on a foundation of cosmic chance? You could see it as the ultimate source of dread, a cosmic nihilism that makes everything pointless. If the universe can be deleted without warning, what's the point of any of it? But there's another way to look at it. A more profound way. The potential instability of the universe doesn't have to erase meaning, it can amplify it. The knowledge that our cosmic home isn't guaranteed makes its present reality infinitely more precious. The universe, through its fine-tuning, gave us the gift of a reality that was stable enough for consciousness to wake up. We are the universe's way of looking back and understanding itself, a brief but magnificent flowering of complexity in a cosmos that could have easily been barren. This leads to a controversial but powerful idea called the anthropic principle. In simple terms, it suggests that the reason we see the universe as perfectly tuned for life is that, if it weren't, we wouldn't be here to see it. It flips the question. We shouldn't be surprised that the laws are perfect for us, because we could only exist in a universe where they happen to be. This idea often leads to the concept of the multiverse. Maybe there are countless other universes, each with its own vacuum state and its own laws of physics. The vast majority would be sterile, collapsing in an instant, or remaining a featureless gas forever. And by sheer chance, in a tiny fraction of them, the numbers would land in the narrow, life-giving zone. We, naturally, find ourselves in one of those lucky ones. In this view, vacuum decay isn't a cosmic executioner. It's more like a selection process. Universes that are wildly unstable never get the chance to produce anything interesting. Only those that are either perfectly stable or metastable with an extremely long lifetime, like ours seems to be, last long enough for observers to evolve and ponder their own existence. Whether we are the result of a single, impossibly lucky roll of the cosmic dice, or an inevitable outcome in an infinite multiverse, the takeaway is the same. Our existence is a privilege, not a right. We are the beneficiaries of a cosmic agreement that has held for 13.8 billion years, a stability that allowed matter to organize itself into patterns of breathtaking complexity, culminating in the human mind. The one thing in the known universe that can look at the whole system and ask, why? The fraying of this law, our new awareness of its impermanence, doesn't have to be a source of fear. It can be a call to action. It gives our quest for knowledge a sense of cosmic urgency. We are the universe's attempt to understand its own fragility. Every telescope we build, every particle we collide, every theory we write is a testament to that miraculous, and perhaps temporary, gift of consciousness. Conclusion: we started with a terrifying idea that the single law holding reality together might be coming undone. We journeyed from the shocking precision of the universe's constants to the deep, quantum foundation they spring from. We stared into the abyss of vacuum decay, the possibility that our entire reality is a bubble waiting to pop. And yet, science didn't leave us in the dark. By measuring the very fabric of reality, we've learned that while our universe may not be eternal, it appears to be built to last. We are living in a moment of profound stability, a cosmic golden age. The universe's promise wasn't one of permanence but of possibility. It promised a set of rules stable enough for the miracle of existence to unfold, for stars to light up the dark, for planets to form, and for life to start asking questions. Our existence is the proof that the promise was kept. The deeper question, the one that should guide us, isn't whether the promise will one day be broken, but what we will do with the incredible gift of time it has granted us. The universe gave us a stage. The story we write upon it is up to us. Thanks for watching. If you want to keep exploring the biggest questions in the cosmos, consider subscribing and joining our community. And if you're now wondering about the other ways the universe could end, you might want to check out our video on the ultimate fate of reality. Until next time, stay curious. When the universe deleted its own physics. Alright, let's talk about the laws of physics. They feel permanent, right? Solid. Like they've always been there and always will be. Gravity keeps your feet on the floor, light has its universal speed limit, and the atoms that make you are all playing by a very strict set of rules. We build our entire picture of reality on that foundation. We just trust that the gravity holding our galaxy together today is the same gravity that will be there tomorrow, and the same one from a billion years ago. But what if I told you that trust, that gut feeling of an eternal rulebook, is an illusion? See, the laws we live by? They aren't the original laws of the universe. They're just the ones that survived. In the very first, searingly hot, chaotic moments after the Big Bang, the universe played by a completely different, almost unrecognizably violent set of rules. This is the story of how those ancient, primordial laws died. It's the story of the moment the universe shattered its own rulebook and deleted its own physics. And honestly, it's a bit of a warning, a profound and unsettling reminder that the rules we take for granted today might not be as permanent as we think. The illusion of permanence. So, how can a law of physics just be deleted? First, we have to shake that feeling that these laws are some kind of eternal truth carved into reality itself. Think of it like this. Picture a river. When you go to the riverbank, the water is rushing by, seemingly constant. It looks like the same river every single time, a permanent part of the landscape. But if you actually dip your hand in, the water molecules you touch are completely different from one second to the next. The river's permanence isn't a property of the water, it's a pattern. It's a dynamic equilibrium that only holds steady as long as the conditions, the riverbed, the rainfall, the climate, stay the same. Change those conditions and the river can flood, dry up, or carve a totally new path. The law of the river's flow is completely dependent on its environment. The fundamental laws of our universe work in a shockingly similar way. They're less like commandments etched in stone and more like fragile patterns that pop up and stick around only when the conditions of the cosmos are just right. We are living in a Goldilocks zone of cosmic parameters, and in this zone, a very specific set of rules has crystallized and now governs everything we see. This rulebook is built around four fundamental forces. First up, there's gravity, the universe's grand architect. It's the force that pulls stuff together to make planets, stars, and entire galaxies. It's a long-range operator, shaping the biggest structures in the cosmos with its gentle but relentless pull. Then you've got electromagnetism, This is the force behind light, electricity, and magnets. It's responsible for the structure of atoms, the power running through the device you're watching this on, and the very chemistry that makes you alive. It's the boss of how charged particles interact, giving us a universe filled with light and amazing complexity. Diving deeper into the subatomic world, we find the two nuclear forces. The strong nuclear force is the universe's superglue. It binds quarks into protons and neutrons, and then holds those together inside an atom's nucleus. Its power is unbelievable, but its reach is tiny, confined to the nucleus. Without it, atoms would just fly apart. Matter as we know it couldn't exist. And finally, there's the weak nuclear force. This one is a bit more subtle. It governs radioactive decay, the process where one kind of particle changes into another. It's the force that lets the sun shine, driving the fusion reactions in stars by turning hydrogen into helium. These four forces, gravity, electromagnetism, and the weak and strong nuclear forces, are the pillars of our reality. They call the shots for every interaction, every process, every single thing we've ever seen. They feel absolute and eternal. But the story of our universe is the story of how these four survivors clawed their way out of a much stranger, more unified, and ultimately temporary state of being. To find where our laws came from, we have to go back to a time before they even existed as we know them, to the crime scene of their creation. The first moments after the Big Bang. The crime scene, the first moments. Okay, imagine we could travel back in time. We're flying past the birth of the Earth, past the first stars, past the first atoms, all the way back to just 1 second after the Big Bang. You wouldn't see stars and galaxies. You'd find yourself in a seething, incandescent fog. The temperature is a mind-bending 10 billion degrees Kelvin, so hot that atoms can't even form. The universe is a plasma, a chaotic soup of nuclei and electrons, constantly blasted by a storm of high-energy photons. But that's still not far enough. We have to go further back. Let's rewind to 1/1,000,000th of a second after the Big Bang. The temperature now skyrockets to trillions of degrees. In this heat, not even protons and neutrons can survive. They melt into their building blocks, a roiling, liquid-like soup of quarks and gluons. This is the quark-gluon plasma, a state of matter so insane that physicists at CERN's Large Hadron Collider have spent years trying to create it for just tiny fractions of a second. In this primordial soup, the strong force is basically on mute. The energy is so high that quarks and gluons are flying around way too fast to be tied down. The rules for building protons and neutrons are just ignored, dissolved into meaninglessness by the sheer violence of it all. The force is there, waiting, but the universe is too hot for it to do its job. But even this isn't the beginning. We have to push deeper, to a time so early it breaks our brains and our physics. Welcome to the Grand Unification Epoch, a sliver of time from 10 to the power of 4 cubed to 10 cubed to the power of 6 seconds after the Big Bang. The temperature is an almost nonsensical 10 to the power of 29 Kelvin. In this furnace, the universe is a place of pure, perfect symmetry. The differences between the strong force, the weak force, and electromagnetism completely vanish. They aren't separate things anymore. They merge into a single, unified, grand unified force, governed by one beautiful, elegant symmetry. The particles we know, like quarks and leptons, are basically interchangeable, able to transform into one another with the help of new, super-heavy particles called X and Y bosons. There's no difference between the force that holds an atom together and the one that makes a light bulb glow. There's only one rulebook. And at the very, very beginning, in the first 10 to the power of 4 cubed seconds of existence, the Planck epoch, it's thought that even gravity, the first force to break away, was merged with the others. All four fundamental forces were united into a single, superforce, a state of perfect, pristine symmetry. At this point, our current understanding of physics completely breaks down. Time and space as we know them lose their meaning. We don't have a theory of quantum gravity to describe this. It is the ultimate mystery. So that was the original state of the universe, perfect unity. The laws were simple because the forces were one. But this perfection was fragile, like a pencil balanced perfectly on its tip. It couldn't last. The universe was expanding and, crucially, it was cooling. And with that cooling came the death of the old laws and the violent birth of the new ones. The death of the old laws, symmetry breaking. The story of how our universe got its laws isn't really a story of creation. It's a story of shattering. Physicists call it symmetry breaking, but that clinical-sounding term hides a series of events more dramatic than any cataclysm that came after. As the universe expanded and cooled, the temperature dropped below critical thresholds, and that perfect unity of the forces just became unsustainable. The single, unified rulebook was deleted, and a more complex, fractured set of laws was written in its place. The first crack in that perfect facade appeared at just 10 cubed to the power of 6 seconds after the Big Bang. As the temperature dropped below that staggering 10 to the power of 29 Kelvin threshold, the unified force just couldn't hold itself together anymore. In a cosmic phase transition, kind of like steam condensing into water, the strong nuclear force froze out and separated from the others. All of a sudden, the universe had two sets of rules where before there was only one. The X and Y bosons, the carriers of that unified force, were too massive to exist in this cooler universe, and they vanished, taking with them the ability for quarks and other particles to easily change into one another. The first law was deleted. This event is also what scientists believe triggered cosmic inflation, an absolutely insane period where the universe expanded exponentially, ballooning from smaller than an atom to the size of a grapefruit in a fraction of a second. But the shattering wasn't done. The universe kept expanding and cooling, and the remaining unified force, now called the electroweak force, was itself living on borrowed time. This next split, the electroweak symmetry breaking, is one of the most important moments in cosmic history, and it stars a character you've probably heard of, the Higgs field. In the super-hot early universe, the Higgs field was off. Its value was zero everywhere. And because of that, all particles were massless, just zipping around at the speed of light. Particles like the W and Z bosons, which carry the weak force, were basically identical twins of the photon, which carries the electromagnetic force. They were all part of the same symmetric family. But then, around 10 squared seconds after the Big Bang, when the temperature dropped to about 10 to the power of 15 Kelvin, the Higgs field had its own phase transition. It turned on, settling into a non-zero value that permeates all of space. This broke the electroweak symmetry. As the Higgs field settled, it started interacting with other particles. Some, like the photon, didn't feel it at all and stayed massless. But others, like the W and Z bosons, started to drag against the field. And in doing so, they acquired mass, a lot of mass. This was the moment of divorce. The now massive W and Z bosons became short-range, weak force carriers, while the massless photon remained the long-range carrier for the brand-new, distinct electromagnetic force. The electroweak force was gone, deleted and replaced by its two descendants. With this final split, the four fundamental forces we know today were born. Gravity, strong, weak, and electromagnetic, each with its own rules, its own particles, and its own job to do. The process continued. Around a millionth of a second in, the universe was cool enough for the strong force to finally grab hold of the free-roaming quarks, binding them into the stable protons and neutrons that make up all matter. A few minutes later, those protons and neutrons started fusing to form the first atomic nuclei. The laws that had frozen out of the chaos we're now actively building the universe we know. The rulebook was in place, not because it was written that way from the start, but because the cooling universe fell through a cascade of phase transitions, each one shattering a symmetry and creating a new, more complicated set of physical laws. The ancient, unified physics was deleted, piece by piece. The lingering ghost and the evidence. Okay, this story of a unified past and shattering symmetries is a beautiful theory. But how do we know any of it actually happened? We can't exactly build a time machine and go back to the first picosecond. The evidence, though, is all around us. It's imprinted on the cosmos itself and, amazingly, we've even recreated it in our most powerful experiments here on Earth. The most important piece of evidence is a faint, almost perfectly uniform glow that fills the entire sky. The cosmic microwave background or CMB. This is the universe's baby picture, the afterglow from when the cosmos was just 380,000 years old. Before then, the universe was an opaque fog where photons were constantly bouncing off free electrons, completely trapped. But as the universe cooled to about 3000 Kelvin, electrons were finally captured by nuclei to form the first stable atoms. Suddenly, the photons were free. The universe became transparent, and those liberated photons have been traveling through space ever since, getting stretched out into the cool microwave wavelengths we see today. When we look at the CMB with satellites, we see its temperature is 2.725 Kelvin almost everywhere. That uniformity is huge. It points directly to a hot, dense early state, just like the Big Bang model predicts. But even more telling are the tiny temperature fluctuations, differences of just 1 part in 100,000. These tiny ripples are the fossilized imprints of quantum fluctuations from the inflationary epoch, stretched to cosmic size. By studying the patterns in these ripples, cosmologists can test our models of the early universe with incredible precision. The CMB is the lingering ghost of the Big Bang, and it tells us in exquisite detail about the conditions under which our laws of physics were born. But we can do more than just look at ancient light. We can actually, in a very real way, recreate the conditions of the early universe right here. That's the job of particle accelerators like the Large Hadron Collider, LHC, at CERN. It's a 27-kilometer ring that smashes particles together at 99.999999% the speed of light. When they collide, all the kinetic energy gets converted back into matter and heat, creating a tiny fireball with temperatures not seen since the first microseconds of the Big Bang. In these miniature Big Bangs, we can directly see what matter was like back then. We've successfully created the quark-gluon plasma and confirmed that yep, protons and neutrons do melt under these conditions. And even more importantly, by smashing protons at the highest energies, we can test the unification of forces. The discovery of the Higgs boson in 2012 was the moment it all clicked into place. It was the missing piece that explained exactly how electroweak symmetry breaking happened. Scientists at the LHC produced the W, Z, and Higgs bosons, studied them, and confirmed that their properties matched the theory with stunning precision. In essence, by creating these particles, we are reenacting the electroweak epoch. We are directly observing the components of a reality where electromagnetism and the weak force were one and the same. These experiments turn the abstract idea of symmetry breaking into a concrete, testable, and verified fact. The evidence is clear. The universe we live in is the low-energy, cooled-down remnant of a much hotter, more unified past. The unsettling future, could it happen again? So, the story of our universe is one of cooling down and breaking apart. The laws of physics weren't decreed from on high, they condensed out of chaos. Which brings up a really profound and, let's be honest, deeply unsettling question. If the laws of physics could change once, what's stopping them from changing again? The very same logic suggests our current rulebook isn't final. And there are two main ways physicists think this could play out. One is a slow fade to black, and the other is a sudden, catastrophic rewrite. The first scenario is the heat death of the universe, or the Big Freeze. This isn't a sudden bang, but a slow, grinding slide into darkness over timescales that are just impossible to truly imagine. As dark energy continues to accelerate the expansion of space, galaxies will eventually fly apart from each other faster than the speed of light, leaving our local group of galaxies totally alone in an endless void. Over trillions of years, stars will burn out, leaving a graveyard of black holes and dead stars. But it gets weirder. The theories that predict the unification of forces also suggest that protons themselves aren't truly stable. They are predicted to decay, but with a half-life of at least 10 to the power of 34 years. Over eons, all matter as we know it, planets, stars, everything, will dissolve into a thin soup of light and radiation. Even the black holes will eventually die, slowly evaporating through Hawking radiation over googles of years. What's left is a universe that is vast, cold, empty, and uniform. A void filled with a dilute gas of particles, cooling forever toward absolute zero. At this point, all processes stop. The forces still exist, but they have nothing to act on. Gravity has nothing to pull, the strong force has nothing to bind. The rules haven't been deleted, but they've been rendered completely and utterly irrelevant. The universe ends not with a bang, but with an eternal, silent whimper. The second scenario is way more violent: false vacuum decay. This idea comes directly from what we've learned about the Higgs field. Our measurements of the Higgs boson's mass suggest a startling possibility. Our universe might not actually be in its lowest possible energy state. The Higgs field could be in what's called a metastable, or false vacuum, state. Imagine a ball resting in a small dip on the side of a huge mountain. It's stable for now, but it's not at the true bottom. A much lower, more stable energy state exists down in the valley. All it would take is one good nudge for the ball to roll over the edge and plunge downwards, releasing a massive amount of energy. False vacuum decay theory says our entire universe might be that ball, just waiting for a nudge. Somewhere out there, a random quantum fluctuation could push a tiny patch of the Higgs field over the barrier and into its true vacuum state. This would create a bubble of new physics. Inside this bubble, the fundamental rules would be completely rewritten. The Higgs field's value would be different, which could radically change the masses of particles. The strengths of the forces could change. The very laws of chemistry and atoms that allow us to exist could be erased. This bubble of true vacuum would then expand outward in all directions at the speed of light. We would have no warning. Its arrival would be instantaneous. One moment, our universe is here. The next, it's overridden by a new set of physical laws, and everything inside it is either annihilated or transformed into something totally unrecognizable. While physicists think the probability of this happening anytime soon is astronomically small, the theory itself is a chilling reminder that the stability of our reality is not guaranteed. The laws of physics aren't a solid foundation, but a delicate balance that could, in principle, be tipped over at any moment. Liberation, not nihilism, a new perspective. The thought of our physical laws being temporary, either fading into nothingness or being violently rewritten, can feel pretty terrifying. I get it. It can make you feel like if nothing is permanent, then nothing really matters. It pulls the rug out from under our deepest intuitions about reality. But this idea, as unsettling as it is, can also be profoundly liberating. As people, we chase permanence. We want it in our lives, our work, the things we build. We look to the laws of physics as the ultimate guarantee that the universe is solid and unchanging. It feels safe, like that river that always seems to be flowing. But we know the river is a pattern, not a substance. Its beauty and power come from its constant change. The same is true for the universe. Realizing its rules aren't eternal gods, but are just survivors that are thriving in a very specific cosmic climate. That kills the illusion of permanence, but it doesn't kill the wonder. In fact, it makes it so much bigger. Our universe, with its four forces, stable matter, and capacity for life, exists in this incredibly delicate Goldilocks zone. A little hotter, and atoms would fly apart. A little denser, and it would have collapsed on itself long ago. A different value for the Higgs field, and maybe none of the elements that make you could even exist. From this perspective, every stable second we get isn't a guarantee, it's a gift. The fact that the laws of physics have held steady for 13.8 billion years, long enough for galaxies to form, stars to light up, and for life to emerge on this one little planet, is an absolutely remarkable stroke of cosmic fortune. Our existence isn't some mundane certainty, it's a precious, fragile, and temporary state of affairs. This knowledge doesn't have to lead to despair. It can lead to a much deeper appreciation for right now. It shifts our focus from searching for some eternal meaning to finding meaning in the beautiful, temporary patterns of the present. The laws of physics gave us this moment, this opportunity to exist, to wonder, and to understand the very universe that made us. The ancient laws were deleted to make way for the laws we have now, and one day, these laws too may pass. But the fact that they are temporary makes the reality they have built, the reality we get to inhabit, all the more extraordinary. So the next time you feel the world locking into a sense of forever, remember the river. Remember the quark gluon soup that birthed stars. Remember that the rules we live by are not commandments, but cosmic habits, survivors of a violent past, thriving on borrowed time. They are the conditions that allow for pattern, for structure, and for you. The real question is, what pattern will you shape while these conditions allow? If you enjoy having your reality completely flipped on its head and want to explore more of the deepest mysteries of the cosmos, make sure you subscribe and hit that bell so you don't miss our next journey into the unknown. And let me know in the comments, does the idea of temporary physical laws make you feel anxious or awestruck? Conclusion: our universe is a story written in disappearing ink. The first chapters, penned in the language of a single, unified force, have long since faded away, replaced by the more complex syntax of the four forces we know today. We are living in one of these later chapters, a period of incredible stability that has allowed for all the complexity and beauty we see around us to emerge. But the story isn't over. The ink is still fading, and future chapters might be written in a language we can't even begin to comprehend. Recognizing this doesn't diminish the story. It makes our part in it, our brief, fleeting moment to read the words and marvel at the tale, infinitely more precious. The laws may not be permanent, but the wonder they inspire in us can be. The universe's accidental self-destruct code. In our search to understand the universe, we often look for fundamental rules. One of the first, and perhaps most important, that we discovered was the law of conservation of energy. That it can neither be created nor destroyed. It suggests a kind of perfect balance, a foundation for cosmic stability that governs everything. But what if this principle wasn't a grand design for permanence, but simply a starting condition? An accidental outcome of the universe's first moments that, when paired with another, more subtle law, dictates a final and inevitable end. This isn't a story of a sudden event, but of a quiet, steady process programmed into the fabric of reality from its very beginning. It is the story of how one of the universe's most basic rules became a pathway to its own dissolution. The principle of balance. As we try to make sense of the cosmos, we look for patterns, principles that seem unchanging and absolute. We sometimes imagine the universe as a system running on an underlying code, and the law of conservation of energy seems to be one of its most foundational lines. The concept itself is straightforward. The total amount of energy in a closed system remains constant. It only changes form. All the energy that has ever existed is still with us, and all the energy that will ever exist is already here. Consider a sealed jar of fireflies. As they light up, they convert the chemical energy in their bodies into light and heat. The total energy within the jar, chemical, light, thermal, kinetic, remains precisely the same. The account is always balanced. This principle is at work everywhere. Energy from the sun, born from nuclear fusion, travels across space to a leaf, where it is converted into chemical energy through photosynthesis. An animal might eat that leaf, converting the plant's energy into the kinetic energy of motion and the thermal energy that warms its body. When we charge a device, we are taking electrical energy that was converted from another source and storing it as chemical potential in a battery. A dead battery isn't truly empty. Its useful chemical energy has simply been transformed into the light of a screen and the heat it gives off. From the smallest quantum level to the collision of galaxies, the universe seems to be a very careful bookkeeper. It's this reliability that gives us a sense of underlying order, a feeling of stability. It suggests a system that is robust, perhaps even eternal. If the universe cannot run out of energy, it seems reasonable to think it can't ever truly end. It can only change. But this perception of the law as a guarantee of immortality may be an illusion. What if the law is not a design, but simply a condition that fell into place by chance? We see a rule that implies an eternal balance, but it also describes a closed system with a finite budget, from which there is no escape. And inside this sealed cosmic environment, another law is at work, one that uses this perfect balance to bring about a slow, irreversible decay. The very rule we thought might guarantee a forever is, instead, the first part of a sequence leading to an inevitable end. The cosmic starting condition. To understand how this came to be, we have to go back to the very beginning of cosmic time, to a moment before the rules we know had settled. In the first fraction of a second after the Big Bang, the universe was in a state almost beyond our comprehension. A dense, intensely hot cauldron of pure energy. In this state, the four fundamental forces of nature are thought to have been merged into a single, unified force. The line between matter and energy was indistinct. It was a realm of pure potential, a kind of chaos without a settled structure. The laws of physics as we know them were not pre-written. Instead, as the universe began to expand and cool, it seems to have gone through a series of phase transitions. This is similar to how water, as it cools, freezes into the ordered, crystalline structure of ice. The specific pattern of the crystal is a consequence of the conditions under which it froze. In the early universe, something analogous seems to have happened. As the cosmos cooled below certain temperature thresholds, the unified forces froze out, separating to become the distinct forces we see today. The fundamental constants of nature, the speed of light, the strength of gravity, settled into their present values. As far as we can tell, these values appear arbitrary. They didn't have to be what they are. In that initial moment, the universe's total energy budget was also established. The law of energy conservation wasn't a decree, but simply a description of these starting conditions. The universe began as a closed system and has, for the most part, remained one ever since. The vault was filled once and then sealed. This was not the only possible way a universe could have formed. One could imagine a cosmos where energy could appear and disappear at will. Such a place would likely be too unpredictable for stable structures like atoms or stars to ever form. Our universe, by chance or otherwise, settled on a more stable path. It began with conservation, but this condition had a profound and inescapable consequence. By becoming a closed system, the universe also became subject to the laws of thermodynamics. And while the first law describes the closed container, it's the second law that seems to determine the fate of everything inside it. The condition that allowed for stability also set the universe on a one-way path, leading from its high-energy birth toward a quiet and very cold end. Humanity's discovery. For almost all of human history, this fundamental rule operated unseen. The story of how we uncovered it is one of slow, gradual realization, pieced together from observations of cannon manufacturing, medicine, and the repeated failure to achieve an old dream. The idea that nothing can be created from nothing is an old philosophical assertion, but the scientific investigation began in earnest during the Industrial Revolution. With the rise of engines, many became captivated by the idea of a perpetual motion machine, an engine that could create its own energy and run forever. For decades, inventors attempted to build such a device, using clever arrangements of wheels, levers, and magnets. They were, in a way, trying to find an exploit in the operating system of reality. And without exception, they all failed. The universe consistently refused to provide a free lunch. This pattern of failure was the first real clue that a firm rule was in place. The nature of this rule was first glimpsed by someone who wasn't looking for it. In 1798, Benjamin Thompson, Count Rumford, was overseeing the boring of cannons. He noticed that the process generated an immense and seemingly limitless amount of heat, as long as the work of drilling continued. The prevailing theory was that heat was a fluid called caloric, stored in objects. But Rumford concluded that heat was not a substance being released, but a form of motion being generated. Decades later, in the 1840s, a German doctor named Julius Robert von Mayer made another connection. He observed that the venous blood of sailors in the tropics was a brighter red than in colder climates. He reasoned that because their bodies needed to generate less heat to stay warm, their metabolisms were doing less work. He linked metabolism, heat, and physical work in a chain of transformations. It was the English physicist James Prescott Joule who quantified the relationship. In a series of famously precise experiments, he used a falling weight to turn a paddle wheel in water, and he measured the exact, corresponding increase in the water's temperature. He demonstrated that a specific amount of mechanical work was converted into a precise amount of heat. He had measured the conversion rate. Finally, scientists like Rudolf Clausius and William Thomson, later Lord Kelvin, formalized these observations into the first law of thermodynamics. They hadn't invented a law, they had discovered a pre-existing condition of the universe. Their work revealed that phenomena like heat, light, and motion were all different forms of a single, quantifiable thing: energy. And the most important property of this energy was that its total amount was fixed. Humanity had finally read one of the foundational lines of the cosmic code, but it would take more time to understand its full implications. The second law. The discovery of the first law of thermodynamics established a firm foundation for physics. It described a universe with a fixed energy budget, which seemed to imply that the cosmic engine could run forever, just transforming its energy between forms. But another law was already known, one that governs not the quantity of energy, but its quality or usefulness. This is the second law of thermodynamics, and its central concept is entropy. The second law can be stated simply: in any closed system, the overall quality of energy degrades over time. Imagine pouring a cup of hot coffee in a cool, sealed room. The first law is upheld: the total energy in the room remains constant. But the heat naturally flows from the hot coffee into the cooler air until everything reaches a single, lukewarm temperature. All the energy is still there, just as the first law states. But it is now dispersed, disorganized, and no longer useful. You cannot run an engine on the temperature difference between the coffee and the air, because that difference no longer exists. The potential to do work has been lost. This inevitable slide towards uselessness is an increase in entropy. Entropy is a measure of disorder or randomness. The hot coffee is a more ordered, low entropy state because its energy is concentrated. The lukewarm room is a more disordered, high entropy state. The second law says that entropy in a closed system tends to increase. Every spontaneous process pushes the system toward greater disorder. You can create a local pocket of order, like a refrigerator making ice, but only by expending energy that creates an even greater amount of disorder elsewhere, in the form of heat pumped into the surrounding environment. Now, we can connect this back to the starting conditions of our universe. The first law establishes the closed system. It draws a boundary around our reality and states that the total energy inside is fixed. The second law then describes what happens inside that system. Every event, every star that shines, every planet that forms, contributes to an overall increase in disorder. This is the two-part mechanism. The first law provides the container, and the second law dictates that the contents will decay into a state of uniform equilibrium. Every star is a brilliant, temporary pocket of low entropy, creating order by fusing atoms. But in doing so, it radiates enormous amounts of disordered heat and light, massively increasing the total entropy of the universe. Life itself is a remarkable feat of organization. But to maintain our ordered bodies, we must constantly consume energy and, in the process, release heat and waste, increasing the overall entropy of the cosmos. Every ordered structure, from a galaxy to a living cell, is like a temporary eddy in a river that is flowing steadily towards a sea of equilibrium. They are complex and fleeting, paid for with a larger debt of disorder. The very law of energy conservation, by fixing the total budget, makes the second law's progression toward maximum entropy and inevitability. The long countdown. This process isn't sudden. It is a slow, almost unimaginably long decay that unfolds across distinct cosmic eras. We are currently living in what is called the stelliferous era, the age of stars. The universe is still relatively young and filled with concentrated energy. Gas clouds are still collapsing to form new stars, which in turn forge the heavier elements needed for planets and life. But this is a temporary phase. The rate of star formation already peaked billions of years ago and has been declining. Perhaps 100 trillion years from now, the stelliferous era will end, and the degenerate era will begin. By then, star formation will have stopped. The last red dwarfs, the longest living stars, will have flickered out. The universe will become a dark realm of stellar remnants, cold black dwarfs, dense neutron stars, and black holes, all moving quietly through the growing darkness. The first law is still in effect. The universe's energy is still present, but now locked away in these cold, compact objects. The second law, however, continues its work. Even these seemingly permanent objects may not be eternal. Some theories suggest that protons themselves might be unstable and will decay over timescales of 10 to the power of 36 years or more. If this is true, then all matter made of protons and neutrons would eventually disintegrate into a thin wash of other particles. The final structures will be the black holes. But even they are not forever. As Stephen Hawking described, black holes are thought to slowly lose mass by emitting a faint glow of particles, now known as Hawking radiation. This is an incredibly slow process. A black hole the mass of our Sun might take 10 to the power of 67 years to evaporate. The supermassive black holes at the centers of galaxies could last for 10 to the power of 100 years. Eventually, though, the last and most massive black hole in the universe will radiate away its final particle. It will return all the energy it ever contained back into the cosmos, upholding the first law. But it will return that energy in its most degraded and disordered form, a faint whisper of low-energy photons. The countdown will be over. The final state. This brings us to the end of time. The final state of the universe is predicted by these laws. It is often called the heat death. Despite its name, it is a state of absolute cold and quiet, sometimes called the Big Freeze. After the last black hole has evaporated, the universe will be a vast, expanding, and almost featureless void. It will be populated only by a sparse, drifting fog of fundamental particles, so far from one another that they will almost never interact. The temperature will have reached a near-perfect equilibrium, just a fraction of a degree above absolute zero. Because there are no temperature differences, no work can be done. All physical processes will cease. The flow of time itself, which we measure by the sequence of events, will lose its meaning. There is a before, but there is no after, because nothing will ever happen again. This is the state of maximum entropy. The universe is perfectly and eternally disordered. And yet, the first law remains unbroken. All the energy that existed at the Big Bang is still present in this cold, dark void. It has not been destroyed, it has simply been rendered completely and permanently useless. The energy that once powered stars and life is now a faint, uniform background with no structure and no potential. The process that began with the universe's initial conditions has reached its logical conclusion. The universe has not been destroyed, but it has ended. It exists, but it no longer happens. The cosmic caveat. It's important to approach this forecast with a degree of scientific humility. The story of heat death is the most direct extrapolation of the laws of thermodynamics as we currently understand them. It is the leading theory for the ultimate fate of the cosmos. But cosmology operates at the frontiers of our knowledge, and those frontiers have many uncertainties. For one, there's a wrinkle in the first law itself. While energy conservation is a solid rule in all local experiments, its application to the expanding universe as a whole is complicated. In Einstein's general relativity, as space expands, the light from distant galaxies is stretched, and its energy decreases. It is not clear where this energy goes. This suggests that, on the largest cosmological scales, energy conservation might not be as simple as it is locally. This doesn't necessarily save us from a cold end, but it complicates the picture. Furthermore, our understanding is dominated by a major unknown, dark energy. This is the mysterious influence that is causing cosmic expansion to accelerate, and it makes up about 70% of the universe. The heat death scenario assumes dark energy as a cosmological constant, an unchanging property of space. But what if it isn't? Some ideas, like quintessence, propose that dark energy could change over time. It might weaken, possibly leading to a big crunch, where the universe collapses back on itself. Or, it could grow stronger, leading to a big rip, where the expansion becomes so powerful it tears apart galaxies, stars, and even atoms. Other, more speculative possibilities include a vacuum decay, where a sudden phase transition in space itself would rewrite the laws of physics. So, is the path set by thermodynamics the final story? We cannot say for certain. The heat death is simply the most logical path based on the physics we know best. It is the default fate, unless some other, stranger physics takes over. Conclusion. Meaning in a finite cosmos. We've journeyed to a potential end of everything, to a cold and silent eternity that follows from what may be a fundamental, accidental condition of reality. It's a grand story that ends not with a dramatic flourish, but with a quiet settling. So what are we to make of this? If the entire cosmic project is fated to dissolve into a uniform, useless haze, does that make everything meaningless? Perhaps the opposite is true. The knowledge that our era is temporary doesn't have to lead to despair. Instead, it can give what we see a profound sense of value. We are not living in the final twilight of the cosmos, but in its brilliant morning. We are alive during the stelliferous era, the brief and special time when the universe is filled with light, complexity, and the potential for life. This period of warmth and activity is a fleeting exception in the vast expanse of cosmic time. The fact that this epoch is temporary can make it feel more precious. The universe, through us, has become aware of itself. We are collections of ancient matter, animated for a brief moment, with the capacity to wonder, to create, and to understand the very laws that may one day lead to this quiet end. Meaning may not be found in some imagined eternity, but in our improbable and temporary presence here. We exist as a brief moment of awareness, the universe's way of observing its own quiet and fleeting beauty. If you find these explorations of the cosmos as fascinating as I do, consider subscribing for more journeys into what we know and what we don't. And I'm curious to hear in the comments, does thinking about a finite universe change how you see our place within it? Scientists just detected stress at the edge of reality. We have long been told a simple story about our universe. That it is expanding, pulling everything apart, uniformly, in every direction. It's an elegant picture, one that has defined our understanding of the cosmos for nearly a century. But what if that story is incomplete? What if the universe we see is being shaped by forces we can't? New data suggests a deep inconsistency in the cosmos, a kind of cosmic stress, that may be the first sign that our most fundamental model of reality is beginning to break down. Cosmology, it seems, is in a quiet state of crisis. The smooth, simple universe. For the better part of a century, our map of the cosmos has been built on a single, profound idea: the cosmological principle. It is a formal name for a rather simple assumption that if you zoom out far enough, the universe looks basically the same from every vantage point. The distribution of matter is even, or homogeneous, and the view is the same in every direction, or isotropic. This principle has been the quiet bedrock of modern cosmology, the starting point for almost every theory we have devised to explain our place within the universe. It was not always this way. In the early 20th century, the prevailing view, even one held for a time by Albert Einstein, was of a static and eternal universe. When his own theory of general relativity suggested a dynamic cosmos, one that must either be expanding or contracting, he added a cosmological constant to his equations, a mathematical fudge factor to hold the universe still. It was a decision he would later call his biggest blunder, because the first clues of an expanding universe were already beginning to surface. That evidence first came from an astronomer named Vesto Slipher, who in 1912 noticed that the light from distant galaxies was consistently stretched to longer, redder wavelengths. A redshift that suggested they were moving away from us. But it was Edwin Hubble who, in 1929, brought the pieces together. Through meticulous observation, he uncovered a stunning relationship: the farther away a galaxy is, the faster it appears to be receding. The conclusion was inescapable. The universe was not static, it was growing. This discovery laid the foundation for what would become the Big Bang Theory, the idea that our universe began its life some 13.8 billion years ago in an incredibly hot, dense state. The common analogy is a loaf of raisin bread baking in an oven. As the dough itself expands, every raisin moves away from every other. From the perspective of any single raisin, all the others seem to be rushing away, and the ones farthest away appear to move the fastest. In this picture, the raisins are galaxies, and the dough is the fabric of space itself. There is no center to this expansion, it is happening everywhere at once. For decades, this picture of a uniform expansion was beautiful in its simplicity. It was governed by a single number of immense importance: the Hubble constant, which tells us the rate at which our universe is growing. All of cosmology seemed to hinge on pinning this one number down. If you could get the Hubble constant right, you could determine the age, the scale, and perhaps even the ultimate fate of the cosmos. The universe, it seemed, was knowable. But as our instruments grew more powerful, allowing us to see deeper into space and further back in time, we began to see the first hints of a problem. The first quiet cracks in this perfect picture were starting to show. The first cracks in the picture. The story of our universe is a detective story, and for a time, the clues all pointed to a simple case. After Hubble's discovery, the main question was whether the expansion would go on forever, or if the gravity of all the matter in the cosmos would eventually slow it down, stop it, and maybe even reverse it in a big crunch. To find out, Astronomers needed a way to measure the history of cosmic expansion. They needed to look deep into the past. To do this, they required reliable cosmic mile markers, what astronomers call standard candles. A standard candle is any object whose true, intrinsic brightness is known. If you see a candle in the darkness, you can calculate how far away it is by measuring how dim it appears. For cosmology, these candles were found in the brilliant deaths of stars, type Ia supernovae. These are stellar explosions of remarkable consistency. They occur when a white dwarf in a binary star system pulls too much material from its companion, grows beyond a critical mass, and ignites in a thermonuclear detonation. Because they all explode in almost the same way, their peak brightness is incredibly reliable. They are fantastically bright candles, visible across billions of light years. In the late 1990s, two independent teams of astronomers used these supernovae to measure the universe's history. They painstakingly scanned the skies, found dozens of these distant explosions, and measured their distances. What they found was not just surprising, it seemed impossible. The data from both teams showed the same thing. The distant supernovae were dimmer than they should have been. This meant they were farther away than a decelerating universe would predict. The only way to explain this was if the expansion of the universe was not slowing down at all. It was speeding up. This 1998 discovery was a profound shock. It was like throwing a ball into the air and watching it accelerate upwards into the sky. Some unseen, unknown influence was pushing the universe apart, overwhelming gravity on the largest of scales. Scientists gave this mystery a name, dark energy. It was a placeholder for our ignorance, but it represented a monumental shift in thinking. Einstein's biggest blunder, his cosmological constant, was suddenly resurrected, not to stop the universe, but to explain why its expansion was accelerating. This constant dark energy became a cornerstone of what is now the standard model of cosmology, the lambda-CDM model. But this revelation created a new puzzle. Measuring the Hubble constant became even more critical, and it turns out there are two completely independent ways to do it. This is where the quiet crisis truly begins. The first method is to look at the local universe. Astronomers use instruments like the Hubble and James Webb Space Telescopes to build a cosmic distance ladder. They begin with stars in our own galaxy called Cepheid variables, which pulsate at a rate tied directly to their intrinsic brightness. This allows us to calculate their distance. They then find galaxies that contain both Cepheids and type Ia supernovae. The Cepheids calibrate the distance to the galaxy, which in turn calibrates the true brightness of the supernova. With the supernova's brightness known, we can then use them as standard candles to measure distances to ever more remote galaxies. This method measures the expansion rate as it is today. The second method looks at the early universe, using the cosmic microwave background, or CMB. This is the faint afterglow of the Big Bang, ancient light that has been traveling towards us for 13.8 billion years. Satellites like the Planck Observatory have mapped this light in exquisite detail. These maps showed tiny temperature fluctuations, the seeds from which all future structures, like galaxies, would grow. By studying the size of these ancient fluctuations, physicists can use the well-understood physics of the early universe to predict what the expansion rate should be today. For years, the hope was that these two methods would eventually settle on a single value for the Hubble constant. They have not. As the measurements have become more and more precise, the opposite has happened. The values have drifted further apart. The local measurements from supernovae give a value of around 73 km per second per megaparsec. The early universe measurements from the CMB predict a value of around 67. A difference between 67 and 73 may not sound like much, but in cosmology, it is a profound disagreement. It means the universe around us appears to be expanding about 9% faster than our most fundamental model of physics predicts. This implies that either one of our methods of measurement is flawed, or, far more interestingly, that the standard model of cosmology itself, our grand story of the universe, is incomplete. This disagreement is what scientists call the Hubble tension, and it has brought cosmology to a state of deep and thoughtful crisis. The tension snaps. A crisis in science is often the prelude to a revolution. When a trusted theory begins to fray, it suggests something new is waiting to be found. The Hubble tension has reached this point. For years, scientists on both sides have meticulously re-examined their work, searching for some subtle error. Could our understanding of Cepheid variable stars be wrong? Is there cosmic dust obscuring the light from supernovae in a way we haven't accounted for? With each new measurement, the hope for a simple mistake has faded. The James Webb Space Telescope has remeasured the local universe with unparalleled precision and confirmed the earlier findings. If anything, the disagreement is now sharper. The tension has now surpassed a statistical significance of 5 sigma. In physics, this is the gold standard for a discovery. It means there is only a 1 in 3.5 million chance that this is a random fluke. The discrepancy is real. This forces us toward a stark conclusion. The standard model of cosmology, known as lambda CDM, must be missing something. For 2 decades, this model, built on ordinary matter, cold dark matter, and dark energy, lambda, has been remarkably successful. But the Hubble tension is a dagger pointed at its heart. And so, scientists have begun to explore new ideas. Perhaps dark energy is not constant. One popular idea is early dark energy, a hypothetical field that gave the universe an extra push of expansion shortly after the Big Bang, before fading away. This could alter the conditions of the early universe in just the right way to reconcile the two measurements. Other theories propose new forms of dark matter, or even suggest that our theory of gravity itself needs to be modified. But this is where the story takes an even stranger turn. As scientists have scrutinized the data, a new, more unsettling anomaly has begun to emerge. The Hubble tension is a disagreement about a single number for the universe's expansion. But what if the expansion isn't best described by a single number at all? This idea challenges the cosmological principle itself, the assumption that the universe is isotropic, or the same in all directions. For decades, the incredibly uniform glow of the CMB has supported this principle. And yet, several recent studies, looking at the distribution of distant quasars and radio galaxies, have found hints of what's known as a cosmic dipole. The evidence is complex, but the idea is this: we are moving through space relative to the CMB. This motion creates a dipole pattern in the ancient light. It looks slightly hotter in the direction we're moving, towards the constellation Leo, and slightly cooler behind us. If the universe's matter is distributed uniformly as the cosmological principle assumes, we should see a corresponding dipole in the distribution of distant galaxies, caused by our motion. Several large surveys, however, have found a dipole with an amplitude 2 to 3 times larger than predicted. The statistical significance of this anomaly is still being debated, but for some researchers, it has reached a level that is difficult to ignore. It hints that the matter in the universe might be distributed in a fundamentally lopsided way. It could mean there is a real, intrinsic anisotropy to the universe itself, a preferred direction. This is a deep crack in the foundation of cosmology. It suggests our picture of a smooth, uniform expansion might be an oversimplification. The tension isn't just a number anymore, it may have a direction. And this has led some to wonder if the Hubble tension and this growing evidence for an anisotropic cosmos are connected. The edge of reality. To understand this, we first need to be clear about what we mean by the edge of reality. This is not a physical boundary. The universe, as far as we know, has no edge. What we call the edge is simply the boundary of our observable universe. Because the universe is 13.8 billion years old, we can only see light from objects whose light has had 13.8 billion years to reach us. Anything beyond that cosmic horizon is, for now, invisible to us. Our standard model assumes the universe beyond our horizon looks just like the one within it, homogeneous and isotropic, stretching on and on. But what if that assumption is part of the problem? What if the Hubble tension and the cosmic dipole anomaly are symptoms of the same underlying issue? That the expansion of our cosmic patch is being influenced by something beyond our view? To help picture this, we could think of it as a form of cosmic stress. It's not a formal scientific term, but a way to conceptualize the strain we seem to be observing on the fabric of spacetime. This strain could be caused by several factors, all of which would challenge our standard picture of the universe. One possibility is that our observable universe is not a fair sample of the whole. We might be part of a vast, large-scale structure, perhaps an area of lower density, that is being pulled on by enormous concentrations of matter or superclusters that lie beyond our horizon. We know the cosmic web exists on enormous scales. If our local region is being pulled by a structure so vast we cannot see all of it, it could create a directional bulk flow. This would make our local expansion appear both faster and more lopsided than the true cosmic average. The dipole anomaly could be the evidence for this exact phenomenon. The Hubble tension, in this view, is the measurable effect of our patch of spacetime being stretched by forces on an unimaginable scale. But there is a second, more profound possibility. What if the stress is not caused by something external, but by the physics itself? Here, dark energy is the primary suspect. In the standard model, dark energy is constant. But recent, though not yet conclusive, hints from the Dark Energy Spectroscopic Instrument, DESI, have suggested that dark energy might be dynamic. It may be changing over time. If dark energy is not constant, then our cosmic story becomes far more complex. A dynamic dark energy could create its own kind of stress on spacetime. As the universe expands and the balance between matter and dark energy shifts, the properties of space itself could be subtly altered. This might be why the universe's history, read from the ancient past, seems to disagree with its present. The stress is the signature of this evolving cosmic battle. This line of thought leads to the most unsettling question of all. If spacetime itself can be stressed and strained in this way, it suggests the rules that govern it might be more pliable than we thought. The fundamental constants of nature are what we assume to be the immutable bedrock of reality. But in a universe under this kind of strain, could that bedrock itself be subject to change? This wouldn't be a sudden event, but a gradual shift, first becoming visible at the largest scales and over the longest timeframes. Exactly where we are seeing these baffling anomalies. The Hubble tension, then, might not just be a crisis in cosmology. It may be the first tremor from a fundamental shift in our understanding of reality itself. The fact that scientists do not have the answers is precisely what makes this moment so important. We may be living through a paradigm shift in our understanding of the cosmos, one that could rewrite the foundations of science. This isn't just a puzzle, it's a doorway to new physics, and we are just now turning the handle. If you would like to continue this journey to the frontiers of knowledge, feel free to subscribe. That way, you won't miss what we find on the other side. Conclusion: we began with a simple, elegant universe, a cosmos expanding smoothly and predictably in all directions. For decades, this model served us well. It gave us the Big Bang, a cosmic history, and a sense that we were beginning to truly understand our place within it all. But science is a process of relentless questioning, and as our vision has sharpened, that simple picture has begun to fracture. Today, cosmology is in a quiet state of crisis. The universe appears to be expanding too fast. At the same time, mounting evidence hints that the expansion may not even be uniform, that our universe could be lopsided, with a preferred direction written across the sky. The central pillar of cosmology, the assumption that the universe is the same everywhere and in every direction, is showing cracks. Out of this crisis, a new, more complex narrative is beginning to form. It speaks of a universe not in placid equilibrium, but perhaps under a state of cosmic stress. A tension that might arise from the pull of unseen megastructures, or from the very nature of dark energy itself. Whichever it is, the implication is profound. It suggests we may be seeing the first signs that the fundamental assumptions we've made about the cosmos are incomplete. We are left with a universe far stranger and more mysterious than we had imagined. We look out at the cosmos and see not a finished painting, but a dynamic canvas where the rules themselves are part of the mystery. The old, comfortable map is broken. The path forward is into uncharted territory. And we are here, at this precise moment in cosmic history, to witness it. Scientists find cracks in the arrow of time. We remember what happened yesterday, but we cannot remember what will happen tomorrow. A glass can be shattered, but it cannot be unshattered. We see buildings decay into dust, but we never see dust spontaneously assemble itself into a building. This one-way direction of time, this movement from order toward chaos, feels like a fundamental feature of our universe. It is so deeply ingrained in our experience that we do not see it as a rule, but as reality itself. But what if this is not the complete story? What if the most basic laws of physics, the equations that describe the motion of particles and the orbits of galaxies, are indifferent to the direction of time? At their most fundamental level, they work equally well forwards as they do backwards. A video of a planet orbiting a star is just as believable in reverse. So, where does this asymmetry, this arrow of time, that governs our existence, come from? For more than a century, the explanation has been a single concept: entropy. The idea is that the universe, as a whole, is moving from a state of order to a state of disorder. That is the arrow. But what if this principle, sometimes considered one of the most steadfast in physics, is not absolute? What if, in the quantum realm and across the history of the cosmos, scientists are finding inconsistencies? What if they are finding phenomena that suggest our understanding of time is built on an incomplete foundation? Today, we will examine the law that seems to dictate our past, present, and future. Then, we will follow the clues, the anomalies and puzzles accumulating in physics, that are causing us to ask new questions about the arrow of time. Imagine the universe at its beginning as a place of impossible precision. The second law of thermodynamics is often seen as a relentless process, ensuring that this initial order will eventually give way to a flat, featureless state. This principle, the rule that chaos tends to increase, is what appears to give time its direction. It points toward a distant future of cold, uniform stillness. But what if, within the fabric of reality, this law is not the whole picture? We are not talking about unsupported speculation. We are talking about quiet, persistent questions, debated by physicists at the forefront of their fields, subtle indications that this principle can, under certain circumstances, be part of a more complex reality. The law of cosmic decay. To understand these questions, we must first understand the principle they relate to. This is the second law of thermodynamics, and it is one of the most consequential principles in all of science. At its core, the second law is simple. It states that in an isolated system, a quantity called entropy will tend to increase or stay the same. It does not go down. But what is entropy? A common way to describe entropy is disorder. An intact egg is a low-entropy state. It is ordered and structured. A scrambled egg is a high-entropy state. Its components are mixed and disordered. One can easily turn the low-entropy egg into the high-entropy one, but not the other way around. The universe appears to work similarly. Milk and coffee will always mix. They will not spontaneously unmix into separate layers. When a deck of cards is shuffled, It moves from an ordered state to a random one. The number of ways the cards can be disordered is astronomically higher than the number of ways they can be ordered. Statistically, the universe is always moving into its most probable state, and its most probable state is one of greater disorder. This is a foundation of our reality. It is why things tend to break down and decay. It is why a room, left alone, tends to become messy. This increase in entropy is what many physicists believe gives time its arrow. The past is, by definition, a time of lower entropy. The future is a time of higher entropy. Our experiences of memory and causality are fundamentally tied to this cosmic tendency. This points to a specific fate for the universe, if the second law is an absolute and universal rule, the heat-death. Over trillions of years, all stars would burn out. Black holes would evaporate. All matter would decay into a thin, uniform soup of particles. The universe would reach a state of maximum entropy. With no structure or change, the arrow of time itself would cease to have meaning. It would be an eternal, silent, and unchanging state. This has been the established narrative of time and the cosmos for generations. It is a story of a universe that began in a highly ordered state and is now, slowly and surely, moving toward equilibrium, governed by the second law. It is a powerful story. But the universe, it turns out, may not be so simple. The first clue that something is missing lies not in the distant future, but at the very beginning of time itself. The first anomaly, the cosmic birthday puzzle. The second law describes a one-way path from order to chaos. But this leads to a significant puzzle when we look at the origin of our universe. If things always become more disordered, it implies the universe must have been even more ordered yesterday than it is today, and more ordered the day before. Rewinding the cosmic clock leads to a universe of decreasing entropy, becoming more and more structured as one approaches its beginning. And so, we arrive at the Big Bang. According to the second law, the starting point of our universe 13.8 billion years ago must have been a state of phenomenally low entropy. This is counterintuitive. The Big Bang is often pictured as an explosion, the very definition of a chaotic, high-entropy event. Yet the evidence tells us the opposite was true. Our most important clue comes from the cosmic microwave background, or CMB. This is the afterglow of the Big Bang, a faint light that fills the entire sky. It is a baby picture of the universe at only 380,000 years old. And that picture is astonishingly uniform. Its temperature is the same everywhere to a precision of 1 part in 100,000. This implies the early universe was incredibly smooth and ordered, not a chaotic mess. It was a state of mind-bogglingly low entropy. Why? Why did the universe begin in this highly specific, ordered state, when a chaotic, high-entropy beginning would have been statistically far more likely? This is arguably one of the most fundamental mysteries in cosmology. It is as if you walked into a room to find every air molecule packed neatly into one tiny corner. You would know some process must have arranged it that way. Physicists have developed theories to explain this. The leading one is cosmic inflation. It proposes that in the first fraction of a second after the Big Bang, the universe underwent hyper-accelerated expansion. This process would have taken any initial irregularities and stretched them out, smoothing the fabric of space-time to the uniformity we observe. Inflation is a powerful theory that solves many cosmological puzzles and is supported by data from the CMB. However, it provides a mechanism for the smoothness, but it does not fully explain the ultimate origin of the conditions that triggered inflation in the first place. It shifts the mystery of the low entropy beginning one step further back. The very foundation of the arrow of time, the idea that the universe began in a state of perfect order, is not an explanation, but a deep and persistent puzzle. It is a primordial sign that the rules governing time might be more complex than we imagined. Quantum whispers in the void. The mystery of time's arrow does not only exist at the grand, cosmic scale. It also appears when we journey into the counterintuitive world of quantum mechanics. At the level of atoms and particles, the second law starts to look less like an ironclad command and more like a statistical average. In the world we experience, a vacuum is empty. But in quantum mechanics, there is no true emptiness. Even in a perfect vacuum, space is a foam of quantum fluctuations. Governed by Heisenberg's uncertainty principle, energy can spontaneously fluctuate, even calling virtual particles into existence for brief moments. This is not just theory, these fluctuations have measurable effects, like the Casimir effect, where two uncharged plates in a vacuum are pushed together. These random fluctuations mean that on the smallest scales, the universe is not strictly moving towards disorder. For fleeting moments, in microscopic pockets, order can spontaneously arise from chaos. A random jitter of particles could momentarily arrange themselves into a more ordered state, causing a tiny, local dip in entropy. Globally, the tide of entropy continues to rise, but the fact these dips happen at all is significant. It tells us the second law is not a microscopic rule governing every interaction. Instead, it is a statistical law that emerges from the behavior of countless particles. The universe, at its most fundamental level, is constantly flickering. This idea has been explored further. In February 2025, theoretical physicists published research in scientific reports on time reversal symmetry in certain open quantum systems. While our macroscopic world is dominated by the forward-moving arrow of time, their work explores the theoretical possibility of processes evolving toward states that would appear to us as the past at the quantum level. This does not mean we can reverse time, but it reinforces the idea that the rigid, one-way flow we experience may be an emergent feature of reality, not a fundamental one. This brings us to a famous thought experiment, Maxwell's demon. In the 19th century, James Clerk Maxwell imagined a tiny being that could operate a door between two chambers of gas. By letting fast-moving molecules into one chamber and slow-moving ones into the other, the demon could separate the gas into hot and cold, seemingly decreasing entropy and violating the second law. For over a century, this paradox was resolved by arguing that the demon itself must create entropy to gather and process information. But modern technology has allowed us to build real-life, quantum demons. Recent experiments have created nanoscale devices that use information and feedback to sort particles in ways that test the classical limits of thermodynamics. These experiments confirm that the relationship between entropy and information is more intricate than previously thought. Rather than creating loopholes in the second law, they show that a generalized version, which includes information, is still upheld. These quantum phenomena are another clue. They tell us that the arrow of time is not a smooth, solid line. The relentless march towards chaos is an emergent phenomenon, a macroscopic pattern born from a quantum reality that is far more restless and less committed to a single direction. The black hole information riddle. If the universe's origin presents a puzzle and the quantum world reveals statistical behavior, then black holes represent a place where our two most successful theories, general relativity and quantum mechanics, come into conflict. At the heart of this conflict is the arrow of time. On one hand, black holes are champions of the second law. They take ordered matter, like a star, and crush it into a singularity, a point of infinite density. In this process, the complex information that made up the star is scrambled into a state of maximum entropy. The entropy of a single supermassive black hole can be greater than that of all the stars in its galaxy combined. They are, in a sense, the ultimate triumph of disorder. But here, we encounter a problem. While the second law says entropy and disorder tend to increase, a core principle of quantum mechanics, called unitarity, says that information can never be truly destroyed. If you know the quantum state of a system now, you can, in principle, calculate its state at any point in the past or future. Information is conserved. Black holes seem to challenge this rule. In the 1970s, Stephen Hawking showed that black holes are not truly black. Due to quantum effects at their event horizon, they emit a faint glow of particles, now known as Hawking radiation. Over immense timescales, this causes the black hole to evaporate, leaving behind only thermal radiation. According to Hawking's initial calculations, this radiation is random and contains no information about what fell in. If true, this would mean the information was destroyed, violating a key principle of quantum mechanics. This is the black hole information paradox, one of the deepest problems in modern physics. It is a direct conflict between our theories of gravity and the quantum world. Physicists have struggled with it for nearly 50 years, and the potential solutions are as mind-bending as the problem itself. Some theories propose the information is not lost but is encoded on the event horizon, like a hologram. Others suggest it escapes through subtle correlations in the Hawking radiation. More recent theories propose structures like entanglement islands that could allow information to be preserved. What all these ideas have in common is that they require a radical rethinking of spacetime and information. Black holes are not just objects. They are laboratories where the nature of time is being tested. They show us that the simple, forward flow of time governed by increasing entropy is an incomplete picture. The information paradox is a signpost, pointing towards a new frontier of physics where the arrow of time itself may be redefined. The new frontier, a universe of approximations. We have examined the clues. The highly ordered beginning of the universe, the statistical nature of time at the quantum scale, and the information paradox of black holes. This leads us to a new frontier, where we must reconsider what a law of physics is. Perhaps the second law of thermodynamics is not a rigid, absolute commandment. Perhaps it is what philosophers of science call a ceteris paribus law, a law that holds true, all other things being equal. In an idealized, isolated system, entropy increases. But the universe is not an idealized box. It is a complex, interconnected system. The cracks we've been examining may not be violations of the second law, but glimpses into conditions where all other things are not equal. From this perspective, the laws of physics might be seen as incredibly effective approximations of a reality that is far more complex. Think of a digital map of a coastline. It is a useful model, but if you zoom in, you see it is made of pixels. Zoom in on the real coastline, and you find rocks, sand, and water molecules in constant motion. The law, the smooth line of the coast, is an emergent property, a pattern that appears at a certain scale. Many physicists now believe that time itself might be an emergent property. At the fundamental level of reality, there may be no past or future, but a static, block universe, where all moments exist simultaneously. Our perception of time's flow, our arrow of time, would then be a consequence of our macroscopic point of view. As physicist Sean Carroll notes, the idea that spacetime could be emergent doesn't make it less real, just as a table being made of molecules doesn't stop you from putting coffee on it. If the second law is a statistical approximation and time is emergent, what does this mean for the fate of the universe? The classic heat-death scenario is based on the assumption that the second law is absolute. If it is conditional, other futures may be possible. Recent data has introduced another question into the traditional story. The accelerating expansion of the universe is driven by dark energy. For decades, the leading model assumed this was a cosmological constant. But some recent analyses of data from surveys like the Dark Energy Spectroscopic Instrument, DESI, have raised the possibility of deviations from this constant model. While there is no consensus, these results have led some scientists to revisit the possibility that the repulsive force driving the universe apart could change over time. This reopens the door to a different ending. The Big Crunch, where the universe contracts back into a singularity, possibly leading to a new Big Bang in a big bounce. This paints a picture of a cyclical cosmos, not one doomed to a one-way trip to oblivion. Conclusion: we are at a remarkable moment in science. The story of time's arrow and the universe's descent into chaos is becoming more complex. The questions we have explored, from the quantum to the cosmic, do not mean the structure of physics is collapsing. They mean the building is larger and stranger than we had conceived. The forward march of time, which feels so absolute, might be an emergent feature of our world. The second law of thermodynamics may be the universe's most powerful statistical tendency, but it might not be its final word. We are the observers, and the clues are accumulating, pointing towards a deeper reality where information may never be lost, and where the end might just be a new beginning. What we are discovering is that the arrow of time is not a simple, straight line. It is a complex, frayed, and perhaps even cyclical tapestry, woven from the threads of quantum mechanics, gravity, and information. And we have only just begun to pull at the first thread. What do you think is the most compelling puzzle in the story of time? The beginning of the universe, the rules of the quantum world, or the paradoxes of black holes? Let us know in the comments. The universe is full of mysteries, and the search for answers is the greatest adventure of all. What other cosmic laws might have hidden complexities we haven't found yet? An ancient text predicted when reality's code breaks. Our stories about the end of things are often filled with finality, with collapse. We imagine a big crunch, where the universe implodes under its own weight. Or a big freeze, expanding forever into a cold, dark emptiness. But some ideas, from very different corners of human thought, suggest another possibility. Not an end, but a transition. Not a line that stops, but a circle that completes itself. This is a journey through one of those ideas. It's a story that surrounds a cryptic text, and the complex, modern philosophy that has grown around it. A philosophy that describes reality not as a story of fire and brimstone, but as a vast, predictable cycle scheduled to reboot. The enigma of the manuscript. At the center of this idea is a document known as the Chun-Bu-Kyung. But the moment we try to find its origins, the narrative splits onto two very different paths. One story, told by spiritual thinkers like Ilchi Li, presents the Chun-Bu-Kyung as a piece of primeval wisdom. This tradition claims its origins trace back over 9,000 years to an ancient Korean civilization, passed down orally for millennia from one generation of masters to the next. In this telling, it was finally written down by a legendary scholar named Choi Kai-won in the 9th century, who carved its 81 characters onto a stone tablet. From this viewpoint, the text is a direct transmission from a time when humanity was more attuned to the rhythms of the cosmos. But if we turn to mainstream historians, a different picture emerges. Most scholars find no verifiable evidence that the text existed before the 15th or 16th centuries. They argue there's no concrete link to the 9th century scholar Choi Kai-won, and that the claims of a 9,000-year-old oral history belong to the realm of modern spiritual movements. From this perspective, the Chun-Bu-Kyung is not an ancient artifact, but a more recent work of philosophical and mystical thought. So we have two very different histories for one text. Is it an ancient key to the universe, or a more recent piece of esoteric literature? For our journey, we're going to step into the world of its modern interpreters. We will explore the ideas they have built around it, treating it as they do, as a genuine code. Because whether ancient or new, the philosophy that has been drawn from this text offers a radical vision of reality, one that stands in quiet contrast to our familiar stories of the end. The 81 character code. If you were to write down the operating system of the universe, you'd imagine it would fill libraries. The philosophy built around the Chun-Bu-Kyung suggests it takes only 81 characters. This is the next layer of the puzzle. The text isn't a book of stories or commandments. It has no gods or heroes. Instead, its interpreters see it as a numerical representation of cosmic law. something more like an equation than a story. A compact piece of code that, in their view, lays out the logic of creation, evolution, and return. The name, Chun Bu Kyung, is often translated as the heavenly code, or sacred text of heaven. When you see the 81 characters in their 9 by 9 grid, you are looking at what its proponents consider a mandala of existence. Its language is famously cryptic, and a literal, direct translation is almost impossible. Adherents don't see this as a flaw. They argue the text is meant to be experienced, chanted, and felt, believing the characters themselves communicate the principles directly. The meaning is not just in the words, but in the numbers, the sounds, and the structure. It's like a seed. The 81 characters are the seed, containing the potential for a vast tree of knowledge. It requires an interpreter to plant that seed in their consciousness and allow it to grow. One of the most influential of these modern interpreters is Ilchi Li. It is through his framework that we can begin to explore the core concept, a fundamental rule that describes a cycle beginning with a single number, unfolding into the reality we experience, and, crucially, how that cycle comes to its inevitable conclusion. Unlocking the first rule, the journey from one. So what is this fundamental rule? According to the interpretation we are exploring, it all begins with the number 1. The first character is il, which means one. But this isn't just the start of a count. This is the one, the source, the beginning that has no beginning. Think of it as the unmanifest potential of everything. Before space and time, there was simply one, a state of perfect, indifferentiated unity. The text says, il si mu si il, which is interpreted to mean, the beginning starts from no beginning. It's a paradox at the heart of existence. The ultimate source couldn't have come from anywhere else. It just is. From this state, the first movement of creation occurs. The one divides itself. The text says, il sok sam geuk, meaning, one is divided into 3. In this philosophy, these are Cheon, Ji, and In, heaven, earth, and human. Now, it's helpful not to think of these in literal terms. Heaven represents the immaterial, energetic principles of the cosmos. Earth represents the material world, everything that has form and substance. And then there is human. This is perhaps the most profound part. Human represents the consciousness that stands between heaven and earth. Our bodies are of the earth, made from the elements of stars. But our consciousness has the potential to connect with heaven, to understand the subtle principles of the cosmos. In this worldview, humanity isn't an accident. We are a fundamental component of reality's structure, the point at which the universe becomes aware of itself. This trinity is the essential framework of existence. Creation unfolds through this division, from unity into a trinity. And from this trinity, the process continues, giving rise to the infinite variety of life. It's a journey from absolute simplicity to the near-infinite complexity of the world around us. But this journey of expansion is only half of the story. Section 4. The cosmic ladder, the meaning of numbers. Once the first rule is established, the one splitting into 3, the code, as interpreted, describes a universe that evolves through stages. This evolution is explained through the language of numbers. If the journey from 1 to 3 is the birth of the universe, the numbers that follow are the story of its life. This philosophy sees the cosmos moving through a great cycle of growth, maturation, and return, from 1 to 9. Each number represents a different phase. Think of it like a cosmic ladder, with each rung taking reality to a new level of development. After the initial trinity, the numbers 4, 5, and 6 are said to represent the stabilization of the physical world, the stage where the laws of physics create a stable framework for existence. Then come the stages of 7, 8, and 9. This is the phase of maturation and, eventually, over-ripening. 7 is seen as a number of spiritual awakening. 8 represents expansion to its maximum potential. And then there is 9. In this system, 9 is the peak. It is the number of maximum development, maximum complexity, and maximum manifestation. The journey of expansion that began with 1 has reached its absolute zenith. Think of a tree. It begins as a single seed, 1, grows a trunk and branches, 3, and reaches its full, magnificent size, 9. Then, with the coming of winter, it lets go and enters a period of dormancy, ready for a new cycle. This numerical progression suggests that the universe is not static, nor is its expansion endless. It follows a defined path of growth that leads to a peak. And the critical question this forces us to ask is, what happens after 9? The peak of existence, the stage of 9. According to this philosophy, the universe isn't just expanding, it's maturing. And that maturation leads to a peak, the stage of 9. A state of maximum complexity, diversification, and tension. So what does it mean for a universe to be in this stage? Proponents of this interpretation look at our world today and see the signs everywhere. They point to the explosion of information, the dizzying complexity of our global societies, the intricate web of technology that connects us all. Humanity's development has reached a point of unprecedented intricacy. This, they would say, is the signature of 9. But 9 is also seen as a number of stress. When a system reaches its maximum complexity, it also reaches its maximum instability. Think about our world. We see unprecedented technological growth alongside an unprecedented ecological crisis. We have more knowledge than ever, yet we often struggle with a sense of meaning. Have you ever felt it? That sense of overwhelming complexity, the feeling that things are moving too fast, that the systems we rely on are becoming strained. According to this philosophy, that personal feeling is a small reflection of a cosmic reality. It's the symptom of a universe that has reached its developmental limit. The environmental crises we face are viewed not just as isolated problems, but as symptoms of a planet reaching the end of a vast energetic cycle. This is where the abstract formula becomes personal. The idea is that we are living through the climax of this cosmic era. We are at the top of the arc. The journey of expansion is complete. And if 9 is the peak, it means there is nowhere else to go but into the next phase. The rule of expansion has run its course. It's not a prophecy of doom, but simply the clock striking 12. It is the arrival of what the philosophy calls the transition. The transition, not an end, but a handover. The idea of a final day brings to mind images of catastrophe. But within this philosophical framework, it means something very different. It is not an event of destruction, but a moment of transition. Not an explosion, but a handover. Contrast this with the endings often discussed in cosmology. The Big Freeze is an end defined by cold and darkness. The Big Crunch is a violent reversal. The Big Rip is a scenario where the fabric of space itself is torn apart. They are all destructive, terminal events. This philosophy describes something else. It is the moment the rule of creation and expansion simply stops applying because the conditions that supported it are no longer present. It's like a software program that has completed its function and now must close. The code doesn't break, it reaches its scheduled conclusion. Think of a tree in autumn. As the days grow shorter, the leaves fall. The tree isn't being destroyed. It is entering a necessary period of rest, letting go of what it created to conserve energy for the winter and prepare for the new growth of spring. The end of the season for the leaf is not an apocalypse for the tree. It is a transition. This is the analogy for the universe. Having reached the peak state of 9, the cosmos is like the tree in late autumn. The energy that fueled its growth is waning. The system is becoming exhausted. The transition is the moment the universe begins to let go. In this view, forms dissolve and structures break down, returning to their simpler states. It is a process of dissolution, not destruction. The purpose is not to annihilate existence, but to return all the energy and matter to the source, so that a new creation can eventually begin. It's a quiet, purposeful transition that reframes our understanding of endings, suggesting they are a fundamental part of an eternal cycle. A scientific parallel, whispers of cosmic cycles. This concept of a cyclical universe might sound like pure metaphysics. And it's true, the Chun Bu Kyung is not a scientific text. Its language is that of spirit and number. But this is where we find a fascinating parallel, an echo of an idea from a very different field, theoretical physics. It comes from the mind of Sir Roger Penrose, in his model called conformal cyclic cosmology, or CCC. To be absolutely clear, Penrose's theory is a complex hypothesis in physics, and he has never made any reference to Chun Bu Kyung. This isn't a validation of the ancient text. Instead, it's an example of how two very different paths of human thought, one spiritual, one scientific, can arrive at a similar, deeply profound concept. Here is the simplified core of CCC. Penrose starts with the widely accepted fate of our universe, the Big Freeze. Trillions of years from now, the universe will be a cold, dark, and empty place. All stars have burned out, all matter has decayed, and even supermassive black holes have evaporated. All that's left is a thin soup of massless particles, mostly photons. But here, Penrose makes a breathtaking leap. In a universe with only massless particles, which don't experience time or scale, our infinitely large, cold, future universe becomes mathematically identical to an infinitely small, hot, dense state, the exact conditions of a Big Bang. Penrose's theory suggests that the end of one universe, its eon, seamlessly becomes the Big Bang of the next. The universe doesn't collapse. It expands to its limit, transforms, and that transformation becomes the seed of the next cosmos. Again, this is a speculative theory. But the parallel is extraordinary. An interpretive philosophy built around a cryptic text describes a universe that reaches a peak, dissolves its form, and returns to a state of potential to begin again. And a Nobel Prize-winning physicist, using advanced mathematics, describes a universe that expands to its limit, dissolves into a state without time or scale, and becomes the beginning of a new cosmos. Both point to the same fundamental idea: the end is the beginning. The return to zero, the cosmic breath. The journey mapped by this philosophy begins at 1 and expands to 9. We've explored the transition not as an end, but as a handover. So, where does this transition lead? It leads back to the beginning. The 10,000 things return to the 3, and the 3 return to the 1. There's another crucial concept here: the return to zero. This isn't the zero of nothingness. It is the zero of pure potential. The unmanifest state that holds the promise of all manifestation. To return to zero is to return to the source code before it is run. Think of your own breath. You breathe in, your lungs expanding to their capacity. This is the journey to 9. Then, you breathe out, letting go until your lungs are empty. This is the return to zero. That pause before the next breath isn't death, it's a necessary part of life. The universe, in this view, breathes. Each cycle of creation is one breath. This process is framed as a kind of cosmic hibernation, where the universe rests and recharges its creative energy. This speaks to a deep human longing for renewal. We all experience cycles of activity and rest, waking and sleeping. This philosophy suggests this rhythm is woven into the very fabric of the cosmos. The universe itself needs to sleep. The return to 1, to 0, is the ultimate act of letting go. It's described not as a loss, but as a homecoming. The final line of the text is often interpreted as, Il Jong Mu Jong Il. The end is the same as no end. The reboot in you. So, we have journeyed through an idea. An idea that begins with a mysterious text, the Chun Bu Kyung, and follows a modern interpretation of its code. A code that describes a journey from 1, the unmanifest source, through the trinity of heaven, earth, and human, to a peak of complexity at the stage of 9. We then reframed the end, not as a terrifying apocalypse, but as a quiet, orderly transition. A cosmic autumn. A scheduled reboot, not a catastrophic crash. We saw a strange and beautiful echo of this idea in the advanced physics of conformal cyclic cosmology. And finally, we followed the cycle to its completion. The return to the 0 point. The cosmic inhale before the next great exhale of creation. What this narrative ultimately offers is a sense of hope. It suggests that chaos and crisis may be integral parts of a much larger, purposeful pattern. The challenges of our time, the feeling of a world stretched to its limits, might not be signs of an impending doom, but the symptoms of a transition into a new beginning. This philosophy places humanity at the center of the story, not as passive victims, but as the bridge between heaven and earth, the consciousness through which the universe experiences itself. And this brings us to a final, lingering question. If this cosmic reboot is not an end, but a new beginning, what does that mean for us, right here, right now? If we are all expressions of the One, experiencing this cycle, what is our role in the universe's next great awakening? What if this reboot isn't something that just happens to us, but something that happens through us? What if the universe forgot how to end? Since the very first moment, the universe has been telling a story. A story of change, of motion, and of becoming. From the first star igniting to the slow dance of galaxies, everything we see is part of this grand, unfolding narrative. But every story ever told, from the smallest to the most cosmic, has an ending. For our universe, that ending has a name: heat death. A final, quiet state where all energy spreads out until everything is uniform, featureless, and still. For trillions of years, this has been the accepted destiny of everything. The story of existence has always been written with a final chapter in mind. But what if, one day, across the unimaginable fabric of space-time, the universe forgot? What if the fundamental principle driving everything towards its conclusion was simply gone? To understand a change like that, we first have to understand the rule itself. It's not something you can see or touch, but you feel its effects every moment. It's the second law of thermodynamics. The physicist Arthur Eddington once called it the supreme law of nature. In simple terms, it says that things tend to move from order to disorder. Think of a hot cup of coffee. The heat doesn't stay in the cup, it spreads into the cooler air. The ordered, concentrated heat gives way to a disordered state of dispersed, lukewarm energy. This relentless march from order to disorder is what we call entropy. This law is more than just a rule about heat. It's the engine of change. It's the arrow of time. The reason you can't unscramble an egg, the reason smoke doesn't gather itself back into a cigarette, is that entropy only moves in one direction. It's this cosmic momentum that pushes stars to burn their fuel and the entire universe to expand toward its final, quiet equilibrium. It is the universe's most unbreakable promise. Until, in our scenario, the rule vanishes. The second law is no more. The arrow of time hasn't just stopped, it has shattered. And what happens to a cosmos that has forgotten its own ending? The answer isn't chaos. It's something else entirely. A profound, absolute, and eternal stillness. The inciting incident, the moment of forgetting. The change wouldn't arrive with a bang. There would be no cosmic announcement. It would happen silently, everywhere, all at once. Imagine a Tuesday afternoon. In a quiet cafe, a cup of coffee sits on the counter. The steam, which had been dancing and dissipating into the air, simply stops. It hangs there, a delicate, frozen swirl, a trace of a process that no longer exists. The coffee itself, which had started its inevitable journey to room temperature, stops cooling. Its warmth is now locked inside it, a permanent state. Across the street, a glass of water is dropped. It shatters, the sound echoing for a moment before something new begins. Silently, with a quiet and unsettling grace, the shards of glass stop their rattling. They begin to glide back toward one another. The splashed water defies gravity, flowing back into the reassembling vessel. In moments, the glass is whole again, as if it never fell. It's not rewinding, it's reordering. This is the first sign. The statistical pressure that said things will almost certainly get messier, not cleaner, is gone. And when that pressure vanishes, the impossibly improbable becomes possible. Smoke from a chimney drifts back down. The random, chaotic motion of air molecules becomes strangely correlated. Heat no longer flows from hot to cold, it simply is. On a grander scale, the planet itself responds. The great rivers that have carved stone for millennia slow their work. The kinetic energy of their water, usually lost to friction and heat, is no longer dissipated. The water flows, but without consequence, without erosion. The great weather engines of our planet, driven by the simple flow of heat from the warm equator to the cold poles, begin to unravel. The jet stream falters. The churning cyclones of the tropics lose their momentum and dissipate into perfectly calm skies. A permanent, windless, and rainless stillness descends on the globe. For people, the first feeling isn't panic. It's a deep, creeping bewilderment. Our most basic intuition, that actions have irreversible consequences, is no longer true. A clock still ticks, but the before and after it measures has become fluid. Memories start to feel different. No longer fixed records of a past that happened, but shimmering possibilities that coexist with the present. Our internal sense of narrative begins to dissolve. We are adrift in an eternal now, where cause and effect is a two-way street. The universe hasn't just forgotten how to end, it has forgotten how to move forward. The immediate aftermath, a sky of crystal. The changes on Earth are strange, but to see the true scale of what's happened, we have to look up. For eons, the night sky has been a canvas of violent, beautiful, and temporary things. But on this night, the view is different. It is static, it is perfect, and it is terrifying. The first thing you'd notice is the twinkling of the stars, or the lack of it. That shimmering is caused by our turbulent atmosphere. With the atmosphere now perfectly still, that turbulence is gone. Every star is a hard, unwavering point of light, like a diamond set in black velvet. But the change goes much deeper than that. The light itself has changed. A star like our Sun is a magnificent engine of entropy. In its core, it fuses ordered hydrogen atoms into more disordered helium, releasing a tremendous amount of energy as photons, light. A star's entire life is a controlled fall towards disorder, a continuous conversion of its mass into energy, all guided by the relentless march of entropy. But now, that march has ended. Deep in the Sun's core, fusion halts, not with a fizzle, but in a state of perfect, unshakable equilibrium. The outward pressure of fusion and the inward pull of gravity lock into a perfect balance. The Sun no longer burns its fuel. It simply glows. It will not age. It will not swell into a red giant. It will not collapse. It is frozen in its prime, an eternal beacon in a timeless solar system. And it's not just our Sun. Across the galaxy, every star, from the smallest red dwarf to the most massive blue supergiant, ceases its life cycle. The universe is no longer a dynamic place of stellar birth, life, and death. It has become a museum of stars. The grand structures of the cosmos follow. We look out to the pillars of creation, the iconic nebula where new stars are forged. These vast, billowing clouds of gas and dust, shaped by the radiation of young stars, are a showcase of cosmic chaos. But now, their dance has ended. The swirling tendrils of gas freeze in place. The entire nebula becomes a static sculpture. The star nurseries of the cosmos have closed, forever. Closer to home, Jupiter's great red spot, a hurricane larger than Earth that has raged for centuries, becomes a permanent, painted-on swirl. On Mars, the dust storms cease. Every grain of sand on every dune is now fixed. The orbits of the planets themselves become unnervingly perfect. The subtle chaos that governs the solar system, driven by entropy on a cosmic scale, is gone. The solar system crystallizes into a perfect clockwork mechanism, a silent, grand orrery suspended in the unchanging light of its frozen star. The sky is no longer a window into a living universe. It has become a static portrait, beautiful and utterly dead. The unfolding consequences, the crystallization of reality. As what we used to call time passes, the true scale of this change reveals itself. The consequences ripple outwards, from stars to galaxies to the very shape of reality. It begins to crystallize. Let's zoom out to the majestic scale of the Milky Way. Our galaxy is a spinning disk of hundreds of billions of stars. Its iconic spiral arms are not fixed things. They're density waves, like traffic jams of stars and gas that move through the disk, triggering new star formation. They are a direct result of the galaxy's dynamic, evolving nature. Without the engine of entropy, the rotation slows, then stops. The spiral arms freeze. The great cycles of a galaxy's life, of gas collapsing into stars, stars living and dying, and their materials forming new stars. This engine of cosmic recycling is shut down. The galaxy is no longer a city, it is a monument. And the black holes? In our universe, they are the ultimate expression of this one-way street of time. But in a universe without that law, their role becomes strange. The process of Hawking radiation, the theoretical mechanism by which they slowly evaporate, is driven by entropy. Without it, the process could become reversible. A black hole might exist in a perfect balance with everything around it, neither growing nor shrinking. These gravitational singularities, once the most destructive forces, become perfect, silent spheres of infinite density, the dark hearts of frozen galaxies. Now, we must consider the grandest scale of all, the cosmos itself. We have known for a century that the universe is expanding. This expansion is tied to the arrow of time. As space expands, the energy within it spreads out and cools, moving the whole universe toward its final state. When the second law is erased, this expansion simply stops. The distance between galaxies becomes fixed. The entire universe becomes a static grid of unimaginable size. At its most fundamental level, the quantum realm, the transformation is absolute. Without entropy to drive processes forward, the constant, simmering activity at the base of reality settles. It is as if the entire cosmos has undergone a phase change, like water freezing into a single, flawless crystal. Every particle finds its place in a vast, interconnected lattice of spacetime. Reality has not just stopped changing, it has crystallized into an intricate, eternal, and silent mathematical structure. The story of the universe hasn't just ended, the book itself has turned to stone. The new, normal, life in the eternal present. So in this silent, crystalline universe, what becomes of life? Of consciousness? This takes us into the strangest territory yet. All life, from a single cell to us, is a temporary island of order in a sea of chaos. We maintain our complex structures by taking in low entropy energy, like food, and releasing high entropy waste heat. It is a constant battle against decay. Aging, disease, and death are all just manifestations of the second law of thermodynamics acting on our fragile bodies. When that law is erased, the battle is won. But it is an unsettling victory. The processes of metabolism, which rely on the flow of energy and the breakdown of molecules, grind to a halt. Cellular structures become flawlessly stable. DNA replication stops making errors. Mutations become impossible. Every part of a living thing is locked into a perfect, unchanging state. Wounds don't just heal, they spontaneously unhappen, the tissue reordering itself. A creature could no longer die of natural causes, because the very concept of cause is now fluid. It is a biological statue. The implications for consciousness are even more profound. Our experience of self is built on linear time. Our thoughts are a sequence, one leading to another, driven by thermodynamic processes in our brain. Without the arrow of time, what is a thought? It could no longer be a fleeting impulse. Perhaps consciousness becomes a single, sustained state. The last thought you had before the change might become your only thought, held for eternity. Or maybe all possible thoughts exist at once, a vast, static web. Your mind would become a landscape, not a journey. You would not think a thought, you would simply be a thought. Imagine a world of 7 billion living statues. People frozen mid-stride, mid-conversation. Not dead, but perfectly preserved. Their eyes are open, but they are not seeing as we know it. Their minds are suspended in a single, timeless moment of awareness. There is no boredom, because boredom requires time. There is no hope, because hope requires a future. There is no regret. There is no suffering, but there is no joy. There is only being. The universe has achieved a state of absolute peace, the peace of a museum after closing time, where nothing will ever happen again. The philosophical implications. For all of our history, we've been shaped by our struggle against the end. We build legacies. We tell stories. The fear of that final, cold heat death gave our brief existence a sense of urgency, of preciousness. We were a flicker of warmth in a vast, cooling darkness. But what if the darkness never comes? What if the universe, in forgetting its end, has stumbled into a different kind of void? We have replaced the terror of an ending with the quiet horror of stagnation. Every concept we use to find meaning, progress, growth, learning, love, these are all processes, not states. A life is a story. In this new universe, the book is open, but the words are frozen on the page. The story can never finish. What is the purpose of a symphony that holds a single, unending note? For eons, the universe was a process. It was messy, chaotic, and violent, but it was alive with possibility. Now, it is a statement. A single, perfect, and eternally unchanging fact. All the infinite possibilities have collapsed into one final, static reality. We spend our lives striving for permanence, but in a universe that has finally achieved it, have we found a kind of heaven, or a prison made of flawless crystal? The ultimate peace is impossible to tell apart from the ultimate paralysis. The universe is saved from its death, but at the cost of its life. It is a perfect, eternal, and exquisitely beautiful corpse. It leaves us with a final question. We always wondered what would happen at the end of time. But perhaps the more important question was this. What happens when time itself is the thing that ends? If the universe forgot how to die, did it also, in that same silent moment, forget how to live? If these are the kinds of questions that fascinate you, that keep you looking up at the sky, consider subscribing for more journeys into the what ifs of our cosmos. And I'm curious to hear from you in the comments. What cosmic rule should we explore breaking next? What happens when reality's main law fails? Some things feel certain. A flower wilts. A star runs out of fuel. We are born, we live, and then we fade. This quiet forward movement, this gentle progression from order toward dust, is so fundamental that we rarely notice it. It is the background rhythm of reality, a current that carries the entire cosmos along. We cannot play the film of our lives in reverse and become younger. We cannot unbreak a glass that has fallen. The past is settled, the future is open, and time moves in one direction. This feels intuitive, but it is also a deep physical law. But what if that law, the one that ensures everything changes and fades, didn't just stop? What if it simply broke, quietly? Not with a sudden flash, not with a sound that echoes across the stars, but with a silent ripple, beginning at the far edges of the universe. A change that moves inward, creating a ghost universe. A place that looks and feels like our own, but does not know that it has been profoundly and permanently altered. What would happen on the day reality's main law fails? To understand what a failure like this would mean, we first have to appreciate the law itself. It's not a rule written down somewhere. It is a statistical pattern woven into the fabric of the universe. Physicists call it the second law of thermodynamics. A more descriptive name for it is the arrow of time. The law says that in a closed system, a measure of disorder, called entropy, tends to only increase. The universe, as a whole, is the ultimate closed system. From its beginning, a state of incredible order and density, it has been on a one-way journey toward a state of maximum disorder, sometimes called heat death. This might sound technical, but it is something you experience every day. Pour milk into coffee. You see the white swirls spread and mix until the cup is a single, uniform color. You will never see that process happen in reverse. You will never see a mixed cup of coffee spontaneously separate back into black coffee and a neat drop of milk. The mixed state is simply more probable. There are many more ways for coffee and milk molecules to be jumbled together than for them to be neatly separated. The universe quietly moves toward its most likely state. That is entropy. Think of a sandcastle on a beach. It is a structure of careful order. Each grain of sand is in a specific, unlikely place. Now, think of the forces acting on it: wind, waves, a passing footstep. For every one way the sand could be arranged to keep the castle standing, there are trillions of ways it could be arranged that lead to its collapse. The castle is not doomed because the universe dislikes sandcastles, but because an ordered state is statistically fragile. A simple pile of sand, a state of high entropy, is overwhelmingly more likely. The castle is a low entropy state. The second law is why a hot object cools down in a room, spreading its heat until everything is the same temperature. The energy does not vanish. The first law of thermodynamics ensures energy is conserved, but it spreads out, becoming less concentrated, less useful. A pocket of concentrated heat is a low entropy state, an opportunity for something to happen. A room at one temperature is a high entropy state, a place of equilibrium where nothing much changes. This is also why every machine is imperfect. A car engine cannot turn 100% of the energy in its fuel into motion. Much of it is always lost as waste heat, which spreads into the air, increasing the universe's total entropy. This principle underpins almost everything. It is why stars shine. They are immense engines turning the ordered matter in their cores into the disordered energy of light and heat, which radiates across space. It is why we age. Our bodies are very complex, low-entropy systems. To maintain this order, we need to take in energy, food, and in doing so, we release heat and waste, increasing the entropy of our surroundings more than we decrease our own. Over time, the quiet pull of entropy, the cumulative effect of countless small, random damages, leads to decay. The second law tells the story of time. It explains why we can remember the past but not the future. A memory is an ordered pattern in the brain. Making it requires energy and increases the total disorder of the universe. The past is the direction of lower entropy, the future is the direction of higher entropy. So when we talk about breaking this law, we aren't just talking about a detail of physics. We are talking about unraveling the flow of time itself, and the relationship between cause and effect as we know it. So, let us imagine it. The break. It does not happen everywhere at once. That would be too simple, too quick. Instead, it begins at a single point, in a place almost impossibly far away. Picture the farthest galaxy we can barely see, a faint smudge of light from near the beginning of time. Now, go even farther, beyond the edge of what we can observe, to a place whose light has not had time to reach us yet. It is there that a single quantum event goes wrong. Perhaps two particles interact. In our universe, the outcome of their meeting has a range of probabilities, all leaning heavily toward increasing disorder. But in this one case, for a reason we cannot explain, the rules themselves change. The universe loses its bias. An outcome that decreases entropy, that creates order from disorder, becomes just as likely as one that increases it. The arrow of time, at this one tiny point, has been broken. This is not a violent event. It is a change in the source code of reality. And it begins to spread. This break expands from its origin point at the speed of light. It is not a wave of energy, but a ripple in the law itself. An invisible wave, rewriting the rules of physics as it passes. It is like a phase transition, the way water quietly freezes into ice. At the boundary, the normal universe gives way to a new, broken phase of reality. The scale of this is hard to imagine. This ripple may have started billions of years ago in a galaxy we now see in its youth. For all that time, it has been spreading, a growing sphere of broken physics consuming everything in its path. From here, we would see nothing wrong. We see that distant galaxy as it was, a snapshot from a time before its fundamental nature was erased. We are watching a ghost, a recording of a place that, in its own time, no longer exists in the same way. The ripple is on its way. It crosses the quiet voids between galaxies. It washes over spiral arms, stars, and planets. And nothing can know it is coming. Because how do you detect a change in the very laws you use to detect things? It is a perfectly quiet apocalypse. It will take eons to reach us, but from the moment of the break, our universe is already living on borrowed time. We just don't know it yet. As this silent ripple expands, it leaves behind a changed cosmos, a ghost universe. For anything living within it, the change might not be obvious at first. But the consequences are profound, moving from the largest scales down to the smallest. Let's trace its path. The first places to be rewritten are those ancient galaxies at the edge of everything. What happens there? A star is a giant fusion reactor, held in a delicate balance. Heat from its core pushes out, fighting the inward pull of gravity. This process is driven by entropy. It turns ordered fuel like hydrogen into a disordered spray of light and heat. When the ripple passes, this drive vanishes. The star doesn't explode. It simply stops. The steady march toward its own end ceases. The fusion reactions become like a coin toss. The star might flicker, its output now erratic, but its fate is no longer tied to the passage of time. It becomes a frozen monument, shining with an unnatural stability, its billion-year lifespan stretched into a strange, static eternity. The cycle of stellar life and death is broken. Elsewhere, vast clouds of gas and dust, the nurseries of new stars, hang in a state of suspended animation. Star formation is a contest between the ordering force of gravity and the disordering force of heat. With the second law broken, this balance is lost. A region of gas might spontaneously grow hotter without a source of energy, pushing itself apart. Another might cool to absolute zero. The forges of the cosmos grow cold. The most quiet and profound change would be to black holes. Black holes are, in a way, the ultimate expression of the second law. But they are not completely black. Stephen Hawking showed that they slowly leak radiation over immense periods of time, a process called Hawking radiation. This, too, is a thermodynamic process. When the ripple washes over a black hole, Hawking radiation stops. The slow evaporation ends. The black hole becomes a perfect prison, a true point of no return. Information that falls in is lost in a way that is fundamentally permanent. From Earth, we would see none of this for millions of years. We would continue to point our telescopes at a galaxy and see it as it was. We would measure its light and map its stars, using a set of physical laws that, for that galaxy, are now extinct. We would be astronomers studying a phantom, documenting the history of a place that has already been overridden. The sphere of broken physics expands quietly. After eons, it reaches our own local group of galaxies. It sweeps through Andromeda. Its trillion stars flicker into their new, timeless state. The light from this event will take 2.5 million years to reach us. For all of human history, and for millions of years to come, we would look up at the Andromeda galaxy, a familiar sight, unaware we are looking at a ghost. The ripple crosses the void between our galaxies. It passes through the cosmic microwave background, the faint, ancient afterglow of the Big Bang. In our reality, this light is slowly cooling. In the path of the ripple, this cooling stops. The echo of creation is frozen. Finally, the boundary arrives at the edge of our own Milky Way. It sweeps through the outer arms, then the inner ones. Star by star, our galaxy is rewritten. The journey from the edge of our galaxy to us, even at the speed of light, would take tens of thousands of years. Entire civilizations could rise and fall on Earth in the time it takes the ripple to cross our own cosmic backyard. And then, one day, it arrives. There is no flash, no earthquake, no sound. The invisible wave front of the broken law passes through the sun, through the earth, and through you. The first clue that something is wrong would be subtle. An experiment measuring radioactive decay, a process governed by statistical laws, would suddenly give impossible results. Half-lives would become meaningless. A block of uranium might decay all at once, or it might reassemble itself from its own decay products. Chemical reactions, the foundation of biology, would become chaotic. A lit match might pull heat from the air, its flame growing cold. A puddle of water might spontaneously gather itself into an ice cube, as the air around it gets warmer. The tendency for energy to spread out is gone. Now, it can just as easily concentrate. A perpetual motion machine would no longer be a fantasy. A device could pull heat from the air to power itself forever. Look up at the sun. Its fusion furnace has burned for 4.6 billion years. Now, it operates under the new rules. The sun might dim, or it might flare violently. More likely, it would settle into a strange new balance, its inward and outward forces perfectly, unnaturally stable. It would still shine, perhaps, but it would no longer be aging. Its journey toward becoming a red giant would be halted. Time, for our star, would have stopped. On Earth, the arrow of time breaks in our daily lives. You drop your phone, and the screen cracks. But now, the state of a cracked screen is no more or less likely than a perfect screen. You might watch as the cracks run backward, vanishing until the screen is pristine again. You pour a hot cup of tea. Instead of cooling, it begins to draw small amounts of heat from the table and the air. Slowly, impossibly, it could bring itself back to a boil. Sound waves might not fade. The words you speak could hang in the air, a pocket of vibrating molecules that refuses to spread out, echoing softly until a random fluctuation finally erases them. This is the ghost universe. Everything around us, the buildings, the trees, the sky, still exists, a legacy of the old laws. But the engine that drove its creation is now broken. The world is running on memory, and its behavior has become unpredictable in a quiet, fundamental way. The link between cause and effect has been severed. In the first moments after the ripple passes, we might not notice. We would go about our day, surrounded by an illusion of normalcy. But the quiet chaos would soon become clear. And it is here, in our own experience, that the true strangeness of a world without the second law would unfold. Our thoughts are thermodynamic processes. To form a memory is to create an ordered pattern of connections in the brain. This requires energy and, following the second law, releases waste heat, increasing the universe's disorder. Life itself is a constant effort to maintain order by taking in energy. When the law breaks, what happens to a mind? Could you form a new memory? Perhaps. But the ordered state of that memory would be no more stable than any other random pattern of neurons. The memory of your breakfast could spontaneously rearrange into a memory of something that never happened. Or it could simply dissolve back into noise. The past, stored in your mind, would become as fluid as the future. Consciousness itself, the steady stream of awareness, could fragment. If the forward flow of time in our minds is no longer a given, our experience could become a collection of disjointed moments. You might feel relief before a problem is solved, or regret for a choice you have not yet made. Your awareness could get caught in a loop, reliving the same few seconds over and over. The idea of a single self, built on a straight line of memory, would begin to fade. The biological processes that define life would no longer be reliable. Digestion, the breaking down of molecules to release energy, is driven by entropy. Without that drive, a meal might provide no energy. Or the process could reverse, with the food in your stomach reassembling itself by drawing heat from your own body. Healing would become a matter of chance. A cut might close, or it might widen. The process of aging, the slow victory of entropy over our bodies, would stop. But it would not be immortality. It would be a state of chaotic change. Your body could grow older by years in one moment, and younger in the next. Death would lose its finality. A dead organism is in a state of high entropy. In the ghost universe, this state is no longer an endpoint. Through sheer chance, the scattered atoms of a decomposed body could reconfigure back into a living thing. A graveyard would become a place of quiet uncertainty, where the dead do not rest, but exist in a state where animate and inanimate are equally possible. Every piece of our technology is designed to use the second law. Power plants, engines, computers, they all work by moving energy from a concentrated state to a dispersed state, and doing something useful along the way. In the ghost universe, the machines we have built would begin to behave in unfamiliar ways. A power plant might start pulling electricity from the grid to reheat its own boilers. A computer might grow cold instead of hot. The flow of energy is no longer a one-way street, and so every machine we have built would fail in a quiet, unpredictable way. Civilization would stop. We could not cook food, purify water, or communicate. Society is a complex, ordered system built on a reliable foundation. When that foundation becomes sand, the structure falls. There could be no planning, no building, no sense of progress. History would end. The true strangeness of the ghost universe is not loud. It is a quiet, creeping madness. It is the loss of the assumption that the world makes sense. It is the experience of living in a reality where the floor might become the ceiling, where yesterday could happen tomorrow, where life and death are a coin toss. It is the final, quiet realization that not only is your existence without a clear direction, but the very concept of direction has been erased from the universe. But of course, the law has not broken. When you let go of a pen, it will fall. Your coffee will cool, and the sun will continue its predictable journey toward its distant end. The arrow of time remains straight. The second law of thermodynamics is not a curse dooming us to decay. It is the very thing that allows existence to be interesting. It is the engine of change, the reason the universe can build stars, planets, and life from the uniformity of its beginning. It's the reason we can learn from the past and strive for a future. The fact that things end is part of what gives them meaning. The sandcastle is beautiful because the tide will claim it. Our lives are precious because they are temporary. If this kind of calm exploration into the nature of our reality helps you unwind, consider subscribing and joining this community of curious minds. These are the biggest questions we can ask, and exploring them together is one of the most incredible journeys we can take. The second law is, in a way, the universe's longing for rest. The ultimate fate of our cosmos may be heat death, a state of perfect balance where energy is so evenly spread that nothing can ever happen again. It will be a cold, dark, and eternally silent universe. But on the long road to that final quiet, this same drive creates pockets of breathtaking order, galaxies, stars, and us. We are the fleeting, beautiful byproducts of the universe's inexorable march toward equilibrium. We are the thoughts the universe thinks on its way to its final sleep. So, the next time you watch steam rise from a cup of tea, take a moment. You are witnessing the engine of reality, the force that gives us a past, a future, and the precious, fragile miracle of now. And it leaves us with one last, quiet question. If the arrow of time were to truly break, what is the very first thing you think you would notice? When a law of physics died and rewrote reality. Before the universe had stars, before it had atoms, and long before the first flicker of light could travel through space, it had a single, quiet law. A unified force that held all of reality in a state of profound simplicity, a principle of almost perfect symmetry. It was the universe's original condition, simple and all-encompassing. But in a fraction of a second, in an event of unimaginable change, that law broke. The perfect symmetry was lost. This was not an end. It was a new beginning. It was the moment reality was rewritten. This single event gave rise to the four distinct forces that would go on to build everything we have ever known, from the galaxies that spiral in the void to the atoms that make up our own bodies. What was this primordial law? Why did it have to break? And how did its disappearance create the beautifully complex, and fundamentally imperfect, universe we inhabit today? Welcome to our exploration of this deep history. If this kind of calm journey into the fundamental nature of our world helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether in a busy city or somewhere quiet, feel free to share where you're watching or listening from. The Age of Perfection, the Electroweak Era. To understand this story, we have to travel back in time. Not just millions of years, but to the very first moments of existence. We are going to a time just 1/1,000,000th of a second after the Big Bang. Forget everything you think of when you imagine the cosmos. There are no silent, dark voids studded with stars. There are no galaxies, no planets, no atoms. Instead, the entire observable universe is compressed into a space smaller than a grain of sand, and it is searingly hot, at a temperature of over 1,000,000,000 degrees. In this environment, nothing we recognize as matter can exist. It is a roiling sea of the most fundamental particles, moving at nearly the speed of light. In this primordial state, however, there was a strange kind of order. A profound simplicity. This order is best described by a word physicists cherish: symmetry. Think of a perfect, featureless sphere. No matter how you turn it, it always looks the same. That is a high degree of symmetry. Now, think of a snowflake. It has a beautiful, six-fold symmetry, but it is more complex. You have to turn it by a specific amount, 60 degrees, for it to look the same. It has less symmetry than the sphere. Finally, think of a jagged rock. It has no discernible symmetry at all. The very early universe was like that perfect sphere. It possessed a higher, more profound symmetry than the universe we live in today. And this symmetry was embodied in its physical laws. While we now experience four fundamental forces: gravity, the strong nuclear force, electromagnetism, and the weak nuclear force, back then, the universe was too hot and too energetic to tell some of them apart. In that first picosecond, two of these forces were unified. Electromagnetism, the force responsible for light and for the very structure of atoms, was fused with the weak nuclear force. The weak force is less famous, but it is utterly essential. It governs certain types of radioactive decay and initiates the nuclear reactions that cause stars like our sun to shine. Without it, the cosmos would be dark. But in that first moment, they were not two forces. They were one: the electroweak force. This was a single, unified law governed by an elegant mathematical structure. This force was carried by a family of four massless particles. Today, we know the carrier of electromagnetism as the photon, the particle of light. The carriers of the weak force are the W and Z bosons. But back then, these four particles were partners in a single dance, all moving through the primordial sea without mass, traveling at the speed of light. Imagine a universe where the mechanism for stars to shine is blended with the force that makes a compass point north. This was the electroweak era. It was a time of pure physics, a state of profound symmetry. But it was a state that could not last. The universe was expanding, and as it expanded, it cooled. And as it cooled, it was about to cross a threshold that would forever change the course of cosmic history. The perfect law was about to break. The shattering, the great cosmic divorce. The end of the electroweak force wasn't a slow decline. It was a phase transition, a change that occurred with unimaginable speed. The trigger was simple: the universe was cooling. As space stretched, the immense energy density of the Big Bang began to thin out. The temperature was about to drop below a critical point. The universe was like steam about to condense into water, and the moment it did, everything would change. This event is believed to have happened in the first trillionth of a second after the Big Bang. The agent of this cosmic change is a character now famous in the story of physics, the Higgs field. It's helpful to think of the Higgs not just as a particle, but as a field. Like a magnetic field, it exists everywhere in space. But unlike a magnetic field, the Higgs is a scalar field, an invisible energy ocean that permeates every point in the cosmos. And it has a very peculiar property. In the extreme heat of the early universe, the Higgs field was in a symmetric state. You can picture it as a ball resting perfectly balanced at the top of a hill. The position is symmetrical, but it's also unstable. In this state, the Higgs field had an average value of 0. The particles of the electroweak force could move through this zero-value field without any interaction, which is why they were all massless. But as the universe cooled below that critical temperature, the Higgs field underwent its phase transition. It's similar to how water, upon cooling, suddenly crystallizes into ice. The Higgs field froze. It settled into a new, lower energy state. But this new state was not zero. The ball rolled off the top of the hill and came to rest in the valley below. This valley forms a circle around the base of the hill, a shape sometimes called the Mexican hat potential. Because the ball could have rolled into any point in that circular valley, the perfect symmetry of being at the very top was broken. The Higgs field suddenly acquired a non-zero value everywhere in space. This spontaneous breaking of symmetry spelled the end for the unified electroweak law. The four force-carrying particles of the electroweak era now reacted to this newly activated Higgs field in profoundly different ways. One of them, the particle we now know as the photon, was special. It did not interact with the Higgs field at all. It sailed through the newly formed Higgs ocean as if it wasn't there, remaining utterly massless. Because it has no mass, it can travel at the maximum possible speed, the speed of light, and its influence can stretch across infinite distances. This is why electromagnetism is a long-range force. Its three former partners, the W and Z bosons, were not so lucky. These particles interacted strongly with the now active Higgs field. As they tried to move through space, they were constantly bumping into it, dragging against it. Imagine trying to run through deep, thick mud. You would be slowed down. This is what happened to the W and Z bosons. They became bogged down by the Higgs field, and in doing so, they acquired mass. They became incredibly heavy, about 80 to 90 times more massive than a proton. This new mass had a dramatic consequence. In quantum mechanics, the range of a force is related to the mass of its carrier particle. Because the W and Z bosons became so heavy, the force they mediate, the weak nuclear force, became incredibly short-ranged, its influence extending only over a distance far smaller than a single proton. This was the moment of the great cosmic divorce. The single, unified electroweak force shattered. In its place, two entirely new and distinct forces appeared. One was the familiar, massless, long-range force of electromagnetism, carried by the photon. The other was the strange, massive, extremely short-range weak nuclear force, carried by the W and Z bosons. The universe's operating rules had been fundamentally rewritten. The single, elegant law was gone. In its place stood a more complex and, as we will see, a far more interesting set of rules. The beautiful, perfect symmetry of the dawn of time was lost, replaced by the broken symmetry that would shape all of cosmic history to come. Building a new reality, the universe we know. The end of electroweak symmetry was not a destructive event, but a creative one. It was the cosmic change that allowed the universe to begin building the complex structures we see today. The consequences of this single event are still unfolding around us, 13.8 billion years later. Let's first consider the force that remained massless, electromagnetism. For the first 380,000 years after the Big Bang, the universe was a hot, dense plasma. In this environment, the newly liberated photons couldn't travel very far. They were constantly being scattered by free-flying electrons, trapped in a glowing fog. The universe was completely opaque. But as the universe continued to expand and cool, another critical threshold was crossed. The temperature dropped enough for protons to capture electrons, forming the first stable, neutral atoms. This event is known as recombination. Suddenly, the fog cleared. The photons were now free to travel unimpeded through space. The universe became transparent for the first time. The light from that very moment is still traveling across the cosmos today. We observe it as the cosmic microwave background, the faint, gentle afterglow of the Big Bang. It is a baby picture of the universe, and it is made of the light set free once atoms could form. From that moment on, electromagnetism was free to do its work. It is the force that binds electrons to nuclei, creating all the elements of the periodic table. It governs how atoms bond to form molecules, giving rise to all of chemistry. Every structure we see, from rocks to trees to our own bodies, is held together by this force, born from a broken symmetry. Now let's turn to the other half of the divorce, the weak nuclear force. By acquiring mass, its carriers made the weak force incredibly short-ranged and, well, weak. But this weakness is deceiving. The weak force is the quiet engine of cosmic creation. Its most important role takes place deep inside the cores of stars. Stars are born as colossal balls of hydrogen. Gravity squeezes the core, making it hotter and denser. But gravity alone cannot make a star shine. For that, you need nuclear fusion. The first step in turning hydrogen into helium, the main process that powers our sun, is to get two protons to fuse. However, two protons will fiercely repel each other. To form a stable nucleus, one of the protons needs to transform into a neutron. This is where the weak force comes in. Through the exchange of AW boson, a proton can change into a neutron. This single, crucial step is the bottleneck in all of stellar fusion. Because the weak force is so weak, this reaction happens very rarely. This is actually a good thing. If the weak force were much stronger, the nuclear fuel in stars would be consumed almost instantly. Instead, its inherent weakness throttles the reaction, allowing stars like our Sun to burn steadily for billions of years, providing the stable energy needed for life to evolve. The breaking of electroweak symmetry, by giving mass to the W and Z bosons, is the reason stars shine instead of just exploding. There's an even deeper consequence. The laws of physics seem to produce matter and antimatter in equal amounts. In the early universe, there should have been a perfect balance, leading to a cosmos filled with nothing but leftover radiation after they all annihilated each other. Yet, here we are. Something tipped the scales, creating a tiny surplus of matter. The precise mechanism, called baryogenesis, is still a major puzzle, but many leading theories suggest the specific conditions created by the breaking of electroweak symmetry were a necessary ingredient for it to work. So, the universe we inhabit is a direct result of this ancient divorce. The existence of light, the formation of atoms, the steady burning of stars, and possibly the very survival of matter itself, all trace their origins back to that one critical moment when a perfect law shattered, leaving behind a beautifully broken reality. The modern quest, echoes of unification. This story of a long-lost law might sound like a creation myth, a tale from a time so remote it's hard to comprehend. But how do we know any of this happened? The answer lies in the incredible scientific structure known as the Standard Model of Particle Physics, and in the machines we have built to explore its predictions. The Standard Model is our current guide to the universe at its most fundamental level. It describes the known elementary particles and masterfully explains 3 of the 4 fundamental forces. The model is built upon the very language of symmetry. And at its heart is the mathematical framework that describes exactly how the electroweak symmetry is broken. For decades, this model was spectacularly successful, but it had a missing piece. The theory required the existence of the Higgs field and its corresponding particle, the Higgs boson. But for nearly 50 years, no one had ever detected one. Finding it became the single most important goal in particle physics. It was the missing keystone of the Standard Model, the physical proof of the mechanism that gives mass to fundamental particles. The quest culminated at the Large Hadron Collider, or LHC, at CERN. The LHC is a 27-kilometer ring designed to smash beams of protons together at nearly the speed of light. In these collisions, for a fleeting moment, the energy becomes so high that it recreates the conditions of the universe fractions of a second after the Big Bang. By smashing particles together with enough energy, physicists hope to knock a Higgs boson loose from its field. On July 4, 2012, scientists at the 2 main LHC experiments, ATLAS and CMS, announced that they had discovered a new particle. Subsequent measurements confirmed that this new particle behaved exactly as the Standard Model predicted the Higgs boson should. It was a monumental achievement. We had, in effect, found the signature of the mechanism that broke the universe's first law. This slow correction of our understanding tells an important story. We worked with incomplete evidence, revised our ideas, and gradually converged on a better explanation. The physics did not change. Our understanding of the physics did. But the story doesn't end there. Physicists are convinced that the Standard Model, for all its success, is not the final word. The dream of unification that drove Einstein for the last 30 years of his life is still alive. The fact that 2 forces were once unified strongly suggests that at even higher energies, in an even earlier epoch, all 3 non-gravitational forces may have also been unified. This idea is known as a grand unified theory, or GUT. Proving this is incredibly difficult. We cannot build a collider powerful enough to directly recreate these conditions. Instead, scientists are looking for subtle, indirect evidence. Some GUTs predict that protons should, very, very rarely, decay. Experiments deep underground are watching vast tanks of water, waiting patiently for understanding to catch up. The ultimate prize is a theory of everything, a single framework that would unite all 4 forces, including gravity. This theory would describe the universe at the moment of its birth. Candidates like string theory exist, but they remain beyond our current ability to test. The journey continues, driven by the echoes of that first broken symmetry. We are listening for whispers from the dawn of time, searching for clues that will lead us back to that state of perfect unification. The future of physics, a second death? We have journeyed back to the past, to the birth of our physical laws. Now, let's journey forward, to the far, far future, and ask a quiet question. If a law of physics could break once, could it happen again? The answer, according to our best understanding of the Higgs field, is a tentative and unsettling yes. The key to this idea lies in the stability of the Higgs field itself. The precise mass of the Higgs boson, which we have now measured, allows us to calculate the shape of that energy valley where our universe rests. And these calculations have revealed something profound. The valley our universe's Higgs field currently occupies might not be the absolute lowest energy state possible. Think of our analogy of the ball on the hill. We thought it rolled down into the deepest possible valley. But what if it only rolled into a small dip on the side of a much larger mountain? This is what physicists call a metastable state, or a false vacuum. It's stable for now, but it's not truly, fundamentally stable. There may be another, deeper valley, a true vacuum, that represents an even lower energy state for the universe. The laws of quantum mechanics are strange. They allow for a phenomenon called quantum tunneling. A particle in a false vacuum state can, given enough time, simply disappear from its current position and reappear in the true vacuum on the other side. It's an incredibly rare process, but over immense timescales, the improbable can happen. If this occurred, even at a single point, it would be the start of a fundamental change. A tiny bubble of true vacuum would appear. Inside this bubble, the Higgs field would have a different value. And because the properties of fundamental particles are determined by their interaction with the Higgs field, inside this bubble, the laws of physics would be completely rewritten. This bubble would then expand outward in all directions at the speed of light. As this wall of change washed over the universe, it would alter everything in its path. The masses of electrons and quarks would change. The delicate balance that allows for stable atoms and chemistry would be gone. Atomic nuclei would fly apart. All the structures built upon our current laws of physics would be dissolved. The universe wouldn't end. It would be reset to a new ground state with a new operating system. A new universe with new physics would emerge. Now, it's important to put this in perspective. First, these calculations are on the very edge of our knowledge, and it's possible that new physics we haven't discovered yet makes our vacuum perfectly stable. Second, even if our universe is in a false vacuum, the estimated lifetime of this state is fantastically long, a timescale so vast it is difficult to comprehend, far longer than the current age of the universe. The probability of it happening anytime soon is practically zero. But as a thought experiment, it is profound. It tells us that the reality we perceive, the laws we have discovered, may not be permanent. They might just be a temporary phase in the universe's long story. The same mechanism that gave birth to our reality could one day erase it and start anew. Conclusion: our journey has taken us from a universe of simple unity, through a quiet shattering that rewrote the laws of existence, to the complex cosmos we inhabit today. We have seen how the breaking of a single law was not an end, but an act of creation. The end of electroweak symmetry gave us light, chemistry, and the power of the stars. It transformed a simple universe into one rich with possibility, a universe capable of producing galaxies, planets, and life. We live in a beautifully imperfect universe. Its flaws, its asymmetries, are the very things that make it interesting. And as we've seen, the story may not be over. It's a humbling and awe-inspiring thought. It reminds us that the cosmos is not a static stage, but a dynamic, evolving entity. The laws of physics are the narrative threads in the grandest story of all. And by continuing to explore these cosmic mysteries, by listening to the echoes of that first broken law, we are slowly learning to read the story of our own existence. If you want to continue exploring the biggest questions about our universe, make sure to subscribe and hit the notification bell. And for your next deep dive into cosmic history, check out our video exploring the incredible theories about what might have existed before the Big Bang.